So today we're going to study the topic on state of health, estimation techniques, battery system mechanisms, and thermal management systems. So let us see what are the contents. So we have the contents of state of health estimation techniques, battery safety mechanisms, thermal management systems. So in the state of health estimations, we need to think about the how the battery health condition would be there for and to give a very life cycle for the batteries, which may would be considered for the lithium ion batteries, and also to see the different mechanisms, how the different mechanisms can be used for the battery safety conditions and also for the health conditions and life also SOE also. Then we have to see about the thermal management, how the systems make use of the battery management systems will take the thermal management very in a positive way for the cooling effects of the batteries when get the battery gets heated up, how the what are different cooling systems we have. That's what we need to study in the thermal management systems. All right. So we just think about the state of health estimations. All right. So state of health estimation is nothing but the how the to how the cells are become to be more very healthy conditions, right? So we need to make the state of health to be more monitored, and also if you want to become the masters in the state of health estimations, we should go for the revolutions of the AI, that is the artificial intelligence and the machine learning, where it is going to make an advanced analyticals which can transfer your understanding into battery degradations. All right. So one thing is that we have to remember here to become the state of health estimations. So we have to carry out the various techniques to analyze the state of health conditions of the batteries and also the state of life of the batteries. How long the remaining useful life would be there for the batteries, so that we have to make the analysis. So in that we have to go for the machine learning, and also we can go for the cognitive learnings. So where you can make use of this analytical systems to make the to become the more understandable for the people, and also we can go for the sustainability for the e-mobilities. All right. So to become a master in SOH, we should have to learn the machine learning and also the AI techniques, which are the different types of AI techniques which are used in the state of health conditions. In the machine learning, also the cognitive learning, the deep learning, right? How it is going to make the analysis, and it will try to give us the analytical data for to make understand to give the take the actions for the remaining useful life. So, all right. So let us see how this will happen. So it will make the degradations of the batteries. All right. So how it is going to make the degradations of the batteries? So let us see. This is one of the most of the, you can say, the most of the the silent killers, where the battery is going to be degraded for a due to the various conditions, right? So that is one about the when you talk about the battery degradation conditions. I was talking about the in the previous sessions. I was talking about how the battery lives can be degraded, right? One is because of the electrodes crack in the electrodes, and also due to the excess of heat in the batteries also, and also during the charging and discharging, that may lead to the crowd of the batteries capacities also, and also it will try to make use of the we need to find out the premature of the risking of the batteries. So that may leads to the hazard of the batteries also, it will not give the safety for us, and also finally it goes for the waste resources which cannot be utilized, right? So for that we need to learn how to work on the degradation, right? So during the time of charging, during the time of discharging cycles, how this can be erode, can a battery capacity can be may have without any accurate state of health of estimation. Well, all right. So we need to see that how the state of health of estimation can be possibilities can be made to make use to understand the concept of degradation, right? So every time when you go for charging and discharging, please see what is the state of health, what is the state of life, what is the state of charging, what is the state of discharging, and what is the state of life. Also, we need to see every time we have to monitor, right? For the time we have to go for the machine learning, so where you can observe all the data, so we can make the analysis and we can understand what action can be taken, right? So every time you have to see the charging and discharging of the cycle silently and also which help us to make the state of health estimation can become more possibilities to understand for us. All right. So which help us to make the risking the premature failure also you can understand. So when the chances of the failure can occur, right? And also we can see the whether it is going to for making any hazardous for the EV also, right? So because of the battery degradation, right? And finally, if the batteries are not used, if we don't make the any action against the degradation, then obviously it will go for the waste resources. So for that reason only we have to see the battery degradation, right? So battery degradation is one of the most of the silent killer which we will not be knowing, right? Which is happening inside the batteries. We have to check what is happening inside the batteries. We have to estimate the battery conditions, right? We have to estimate the health conditions. We have to estimate the charging condition. We have to estimate the discharging conditions, right? So all this comes into the pictures where it will make a lot of impact for the degradations also, and a premature failure also, and also the safety hazard as well as the wasted resources. All right. Now we have to see that why the SOH matters a lot, right? The state of health will matters a lot beyond the battery icons. So when you see the quantifying conditions, right? So we have to see the various conditions of the batteries, right? So before it is going to the proactive maintenance decision, right? It means that when you are taking the predictions, when you are making the prediction of the useful life for the RUL, nothing but the remaining useful life, right? We have to decide that how many life the battery can sustain, right, in the upcoming days, right? So we have to decide the various actions we have to take, right, for the proactive maintenance. We need the decision has to be taken by the users, right? So we have to make the predictions about the remaining life of the batteries, where the batteries can have the precision values. All right. So that means to enable the proactive maintenance decisions, right? So quantifying conditions will tell us about the how the batteries can make the useful life, right? We want to say the remaining life of the battery, right? If we want to say the remaining life of the battery, we have to see the quantifying conditions. All right, we have to make the predictions of the RUL. So when you make the predictions of RUL, no, so we can take the decisions, what decisions we can make to safeguard the battery life conditions, right, in the upcoming days. So that is one reason where we have to see the quantifying conditions. All right. So this is one of the major things, right? So when you study these major things, we'll understand the remaining battery life of the conditions. So here we can say that this is just because of uh, the quantifying conditions where it will tell us about the state of health. It gives a single percentage numbers for the battery health like a just like a medical reports. All right, and we can see that how much of use the voltage and current and temperature. Right, all the data can also be available for that, and we have to think why this is a matters a lot, right? So predicting the remaining life is also always is very very. So you can see there is a remaining useful life, right? So this remaining useful life, for example, if SOH is around 82%, right, and dropping to 2%, 2% per year, right? Then the BMS, we can say the BMS will know say for 1 year, 80% of UL and the remaining will be around. Keep on, it will just keep on decreases as you usage of the batteries will happen, right? So that is the one things where you have to see if in 1 year in the when the it was around 80% of SOH. If you see in the 2 or 3 years, it may come back to it will degrade to the 70% also. Then it will come to the 65%, right? So this is what the remaining useful life, right? In the remaining useful life, the SOH is around 80%, right? The 20% is already gone. If the usage, if SOH is around 70%, it means that 30% of life is already gone, right? The remaining life will be around 70%. That is how the SOH has to be they calculated, right? The one best example you can see that in the Tata Nexon also, right? So where this Tata Nexon of the the SOL life, right? The SOL life is one of the best example, right? Where you can take the EV pack at 75% of SOH, right? So that you can calculate that is the for 75% of SOH if the rating is 30 kVh kW. Okay, sorry, the 30 kW, right? So when you multiply with the 0.75, so what is the life actually left over out of 30 kWh, the life is around 22.5 kWh. So that is called the RUL. That is called the SOH, right? That is called the remaining useful life of the battery, right? So here we can say that if we take the example of 30 kWh, okay, if we take the example of the 30 kWh is the battery ratings, all right. So the remaining life of the SOH is around 75%, right? So when you multiply with in terms of 0.75, multiply with 0.75 with a 30 kWh. So it comes to be around 30 kWh into 0.75. It comes to be around 22.5 kWh. That is the leftover, right? So that is what we can decide the conditions of the batteries. All right. So this is how the SOH can be decided, right? So this plays a very important role in the EV batteries. All right. So when you talk about the maximizes life, right? We have to maximize the life of the batteries, right? So please check every time the premature of the failure of the batteries, and check what is happening inside it. What is the SOH? How much SOH has been dropped, and also how much of the cell SOH has been dropped, and also we have to see we have to prevent the depth of discharge also. Right? That is what we have to observe in the maximizing the life. Right? So it means that we have to see the SOH, the feedback, which can prevent the abuse that kills the battery very early. So that is what you have to see the maximizing the life, right? So it says that SOH, the feedback can be prevents abuse that helps that will kills the batteries very earlier. All right. So let us see the various factors for the maximizing life. Right? Here we can see there is a preventing the premature failure and the optimize the energy delivery across the battery operational life, isn't it? So it means that you have to see what the percentage of SOH has been dropped, right? So if the battery management system which limits the fast charging, like for a C rate is around 20 250 kilowatt to 150 kilowatt, so that will try to reduce the heat. All right. So that is what we have to see the SOH how it is more fasting it is dropping. So all right, yeah, see one cell of SOH is around 85%, but other is 95%, right? So there is a balancing block in your diagrams. What you can see in the previous sessions, all right. As I told in the previous session, one cell will charge for the 85%, one cell will charge for the 50%, other cell will charge for the 35%, right? So this will decide the maximum life, all right. So maximum life of the each cell, if you see the maximum life of the each cell for the under SOH, it is 85%, right? But other cell may have the other may have 90 cell may have the 95%. So what does it mean actually? 85 and the 95% between these two cells. All right. So it means that you are not balancing properly. The cells is not balanced properly, right? That is what we have seen in the previous session. If the cell doesn't balance properly, then the maximum life you cannot expect it, right? So there might be leads to the premature failure. So that may lead to the premature failure of the batteries. So that may optimize your energy densities also. All right. So and also if you prevent from the premature, no, so that you can increase your energy delivery, and also may have the battery optional life will be very good. And moreover, please go check the to prevent the depth of discharge also. That is also very important concept in the maximizing the life. All right. So when you're maximizing in this life now, so you have to see the how the depth of discharge is also happening. So all right. So if you see from your SOS, your state of charge, if you see the state of charge versus the depth of discharge, right? If the depth of discharge kills the life cycle, right? For example, if the depth of discharge kills the life cycle, right? Then the battery management systems may use as the state of health to set the depth of discharge limits. So that is what that will also makes a lot of impact for the maximizing the life of the batteries. All right. So every time you have to see what is happening and what is not happening. So all right. So please go, you have to see over the maximizing the life. That is what you have to check the various conditions of the batteries in most of the times. All right. So next we have to see the how we are going to make the sustainable driver. All right. So this is one of the major and the crucial factors for the most of the EV and for the our green energy. All right. So if the batteries does not go to landfill to 80% of SOH, right? So we have to see what are the impact it is happening on this. All right. So what are the crucial factors? What is the circular economy? So if one EV pack is equal, say one EV pack comes to be around 10 years of car, right? Plus 8 years of grid storage. If you say then it will be would be around of 18 years of total life. So it will give the 18 years of the total life, right? So if you say when you want to get the reduce the waste, right, the 500 kg of the pack mining avoid the per reuse. So that is what when you go for the reusing these batteries, they have to think about the reducing the waste of that much of 500 kg pack of the mining that can avoid for the per reuse. Okay. All right, so this is what you have to think about the more about the why SOG matters a lot in our future. All right, so this is one thing. The batteries has to be reused for the second life also for the application of grid and the backup storage. So that is what I was talking about the how this what is it, enabling the reuse, right? The second life of the application should be there. So if you see in the BMS block, right, in the BMS block, you can go for the cloud IoT for data logging, so that we can check every time the life of the batteries, how it can be used for the various applications for the grid storage and the backup also. Right. So when you come to the point of the traditional approach, right, here you can see there is a different types of the approaches has been undergone. So in the earlier days, we used to have the various kinds of the modeling, the based estimator, right? So we have the IC in the internal combustion engines, right? They were using the relays on electromagnetic models. to see the complexities and as well as the calculation intensive purpose for the real time use. But in case of when we are in the era of the AI and the machine learning, right? So we can see I can take the data of the statistical models, right? Where you can take the model based estimation also you can do with compare with that is more better than the data driven methods, right? So data driven method is more better than the model based estimate, right? Here you can have the statistical models and also the machine learning historical data. That is what you have to collect the past data, then you have to feed to the machine, where the machine will try to understand what actually is happening to analyze and what data it can give and how can be more adaptable for the data driven analysis. All right. So here we have to see more about the why this machine learning has become the more advanced in this era, right? So here we have to see that the deep learning also where you have to think about the linear regressions. All right, you have to think about the linear regressions of the what do you say the fuzzy logic also on the. You can go for the FLC also. You can for testing in the lab also by collecting the data, and also think about the machine learning where you can go for the cognitive learning. Check about the various patterns of the cells, what is happening inside. Then you can see what are the conditions on how it is going to work, right? And check what about the how much of cycle it is collected. And then if you see the collection of the thousand cycles of data, right? Then you fit the curve in the SOH, right? That is you can take the sample of A into cycle plus B into temperature plus E. Then you can see the actual SOH values, right? So that is what the statistical data will tell us. All right. So these are the various things where you have to see about the many major factors why the traditional approach is not compared with the present approach, right? So that is what we have to think about the more about the data-driven methods and the model-based estimators. So all right. So one thing is that what are the key limits? All right. What are the key limitations that we can observe from this? So one thing is that where you go for the both struggling the dynamic current and the white temperature variance and the fluid level complexities, right? So here the modern BMS uses AI with the IoT for the real-time adaptive SOC estimation, right? So that's why you should go for the data-driven method would be very better and far better than the other ones. All right. Let us see how this AI is going to make a revolutions in the world. Okay, so if you see the AI revolutions in the especially in the battery conditions, right? So that is making a lot of impact, right? The machine learning is also making a lot of impact. Where it will try to generate the various kinds of the graphs based on your BMS architects, and also it will try to rewrite the rules for the battery health estimations, so which can deliver the unpredicted accuracy and also scalabilities of the real world applications. All right. Now, using this the AI and the machine learning, what is our core idea? What we have to do from this if we use the AI, right? So AI is also the core idea of the AI is to replace the fixed equations with a learning model, right? Your BMS can act like just like a doctor's, right? It's not a calculator, right? So BMS will try to work with when you implement with the incorporate with the machine learning, right? So BMS will also try to work like a doctor. It will try to understand what action it has to take and what are the machine learning and to apply for this, especially for the battery health conditions. All right. So if you see the various kinds of the rewriting the rules, right? We have the features of accuracies, we have the features of real time, we have the features of adaptabilities, we have the features of the scalabilities, we have the features of handling aging of the batteries, right? So when you talk about the accuracy, right? When you talk about the accuracy of this health condition of the batteries, right? So if you follow the traditional method, right, it may give up to 5 to 10% of SOC error and 8 to 12% of SOC error. Right, if you see of the AI revolution, right, if you see the AI revolutions, it will be around of less than 1% of SOC and 2% of SOH errors. So these are the more of the errors where you can expect in the where in the part of the accuracy. All right. So when you talk about the other factors, right? Which is the other factors we have here? We have the other factors such as I told about the one is accuracy, other is a real time. All right. Then you talk about the real time, right? So in the real time traditional method, here you can see there is a traditional methods and also we have the data driven methods also. When this comparing with these two methods, we can see that there is in the real time traditional model based methods. There will be the too slow of the 5 second of lagging with the charging. And when you talk about the AI revolution, right? If they talk about the AI revolution in the real-time modes, right? LST method, as I talk about the LSTM method, that is the long short-term memory runs in the 50 milliseconds on BMS, that is on the MCU. So, all right. So other factor, when you talk about the other factors, we have the one more factors which is a more important for us to understand. All right. So as I talk about the LSTM is very clear, right? So we think about the other type of the other type of the features. All right. So think about the adaptability, right? If in the traditional methods, it would be the very fixed for the life. All right. So when you go for the AI, then it will learn from the various things, and also it will try to understand. So what is happening actually in the inside the batteries. All right. So it will tell us about the how the batteries can make a perform in the actually in the EV vehicles. So these are very very important things where you have to see the you have to observe the actually the battery life also. All right. So think about the that is the adaptability, right? Which is in the traditional is fixed for a life. If you go for a AI revolution, no, so it will learn from our drawing the with various weather conditions. Will try to understand what is happening and what action it has to take, right? So that is how the adaptability will work, right? When you talk about the scalabilities, right? When you talk about the scalabilities, it is more about the engineers has to tune for each model, right? When the traditional model based method, where if you go for the AI prediction, right? When you go for the AI predictions, one is for the on the cloud. If you pass all the data to the cloud, no AI models, right? It will update some 1 lakh of data at a time, right? Where you can see your example is for your any cars. You can if you upload your data, it will try to understand what is the battery condition, what is the health condition, right? So everything will try to monitor each and every time. All right. So this is the one thing you have to understand why the AI is making the revolutions in the world, right? With respect to our battery conditions. All right. So that is one for the making the predictions and also accuracy, scalability, and the real world applications. So these are the various things where you have to undergo the we have to undergo the various things for the AI revolutionaries. So next is another techniques we have for the graph neural network, right? So these are the various techniques. So where you have to go for the understanding the GNN methods. All right. So GNN method is nothing but it is combining of the LSTM, that is a long-term short memory, right? Keeping the modeling with spatial dependency across the various factors. Correct. So this is the most of the abundant AI methods in our syllabus, right? So this is very important topics where you can see understand the various things of LSTM methods that use the unpredicted accuracies of the battery from the battery. All right. So if the SOH graph is to be, if we show the SOH graph, then we can understand what is LSTM, right? So then we can see why the GNN for the batteries is very very important and what are problems and also how the traditional method of LSTMs can be identified, right? So we have to see that the various the cells, that is if for example if the cell gets 5 cells gets hotted, okay, then 6 cells beside it gets aged faster. So let us take this is the data we are just collecting, okay, for the traditional LSTM method problems, right? So then one more, if you see that there is a weak cell of 12 limits when the whole pack, all cells are get overworked. So this is one of the data we have to see the what are the problems it will occur, right? If it's the temperature, current, aging, all the affects each other. So this is one of the factors, right? So that's why we have to think about the what is happening in the GNN for the batteries. So all right. So if you see the various components and the key factor for this, that is what we have to think about the temporal features of the that is LSTM, the spatial dependencies, and also the self-potential mechanisms. If you talk about the temporal LSTM method, right? So what it does actually, what it does, it will remember the past history like a normal LSTM, right? So temporally LSTM is nothing but for GNN. It will try to remember the past history like a normal LSTM, right? It will take the combine of the LSTM data modeling with the spatial dependency across your health factors, right? When you talk about these spatial dependencies, right? The spatial dependencies how the cell affect the neighbors. So it will tell us about the how the cells are going to affect the neighboring cells also, right? So this is how if one person, for example, if one person is not feeling well, right? So if you sit beside the other person also, he may get the by coughing and sneezing, he may also get kind of the various disease what the other persons has. So similar like that, this is the cells has the problem with aging factor or any other factor, right? Which is not working properly or if you say the cell which gets affected, it also affect the neighboring cells also, right? That is what we have to think about the various the batteries conditions. All right. So this is another things where you have to understand the actual what is happening in the batteries. Okay. So LSTM is a very important method, and also if you see the way LSTM method in form of the matrix, right? That is the RMSC root mean square error values, and also the remaining life of the error. We have to compute and we have to detect the what is happening the LSTM and the GNN plus what attention it has going to be take, right? Then the SOH range if it is around 2.1%, right? And if you see in the GNN, it may be around 0.8%. What is the remaining life of the error? If it is around 112 cycles, right? If it is around to be a 12 cycles, if you say it is around to be a the 12 cycles, so then we can say that the remaining life would be the comes to be around in the GNN, it may be plus or minus 4 cycles. So if we take when it calculate for in the computing its LSTM models, it may be very low, right? If you see the GNN, it may be a very medium also, right? It will be medium. It can runs on the BMS and the MC on your edge artificial intelligence also, right? So these are the various methods we have to undergo we have to see what are the different GNN that is seeing the components. We can see there is a LSTM also. We have the cell protection of GNN. We have the spatial dependency. We have the health factors, and also we have to see the how this it will makes a lot of impact on our battery's health conditions. All right. So that is we have to see about the health factors. We have to check about the health factors, right? So if you talk about the proven impact, right, that may be accuracy and efficiency for the or a standalone LST and also the GRE. All right, let us see the different models which can just given the reference of the one paper. This paper they have made a lot of impact for the improving the accuracy and efficiency of the overall standalone LSTM and the GRE models. All right, so now let us see how this transferring the learning cycle synchronizations will occur. All right, so if you see there is a graphical convolution on it, right? So where you can see there is a RMSC also, right? That is the root mean square. As I told in the most of the paper, the RMS value, that is root mean square error, has to be reduced as much as possible, right? It should be less than 1%. So the problem of the transferring this learning method is to we have to go for the traditional AI problems, right? So that is the GNN as well as the NSTM methods. So you can take the example of the various vehicles such as the Tata Nexon Data and the new Mahindra XUV also, so which has been launched, and also you can take the various for the analysis purpose. All right. So if we talk about the graph convolution network, right? So what does it mean actually? Graph convolution network (GCN), right? Graph convolution network. So GCN, they have told it is leverage the static temporal degradation patterns across the deliver pattern data sets. So it means that the types of GNN, right, that learns the patterns across the different battery chemistries. So that is what it will try to understand. If we apply the AI, it will try to understand the various pattern. It will learn by itself and it will identify the battery chemistry also. What is happening in the battery? It will take the data sets also, right? So that is how the your GNN will work, right? If you say the cycle synchronization, right? If you say cycle synchronization, it will align the charges and discharge of the data from the different EVs to the same scaling, right? That is what we have to see how the cycle synchronization will also happen, right? There is alignment with the cycle of charging and discharging data from the different EVs to the same scale. So just we have to see how this is going to be happen, and we have to see the RMS value also, right? We need to go for the making the analysis. When we do the research, you will understand very clearly. All right. So when you talk about the RMSC, that is the root mean square error. All right. So root mean square error. What it will tell actually? If it is less than 1%. So if it is less than 1%, what is the meaning of it? How does it the BMS will make impact on the RMC if it is less than 1%? So it will tell us about the if SOH is equal to 85%. For example, if you take SOH is equal to 85%. All right. So it means that AI will predict the it will just make a prediction of 84.1% to 85.9%. So that is what the RMS can be identified in a very easier way. All right. This is just because of the how you makes a matters a lot for the GNM. All right. So we have to see how these are the various cycle synchronizations and the learning methods can be happen in the GCN as well as the RMC. RMC will tell us about the, especially RMC will tell us about, it will speak more about the how the actual the life can be would be there for uh, the remaining, that is the SOH. All right. So this is makes a lot of impact for the your temperature conditions also, right, and also the charging and discharging conditions. Right. So we have to think about the cycle synchronization. Why it is needed, right? Why it is very important? Why cycle synchronization is very, very important? If you take for a cycle per day, right? That is a cycle per day. It is around 40% of DOD. For example, if you take a 40% of DOD. So what does it mean actually? If you take example of your Ola taxi or whatever it may be. For EV, I'm just talking about the EV. All right. So if it is a cycle per day, is 40% of depth of discharge, right? So what it will actually? 4 cycles per day, right? Using 4 cycles per day, that is for 80% of our depth of discharge, right? What is the problem existing in that actually? So we have to think about the raw data which cannot be compared with the others, right? And also when you talk about synchronizing the solution, right? That is we have to go from the AI from the AI is from the stretches, how it makes the comparison cycles to the common equipment, life cycles of the skills. So that is why we have to think about the more on the cycle synchronization. All right. So that is also very, very important, the cycle synchronization, where it will make you to understand about the various the things. So next we talk about the charge about the 25% in the night. Okay, if you take charge about the 25% in the night and charge at the 45% in the noon. Temperature, if you see the temperature effect makes it the aging, right? Because there is a change in the temperature in the night and the noon also, right? That is what I'm just thinking about the how the charging will happen with respect to the temperature. There are change in temperature. There is a change in temperature which may affect the aging also, and synchronizations of the to 25 degrees centigrade would be the can be taken as a reference for the making an analysis also, right? So, so that's why the BMS is very important for the analyzing all these the various facts. Right. Let us see the definitions of the SOH. So what is actually SOH? What is the job of the SOH here? What SOH it is doing actually? What is job of SOH? Does it making any job? Right. So that is what you have to understand. What is the job of the SOH for you? All right. So what SOH it is doing actually? SOH definition is nothing but the is a parameter used to indicate the overall condition and aging level of an EV batteries compared to its original one or a new condition. Let us say if the state of health is right, if the state of health is around to be 80%, right? If you say now, if I say, so if I say the state of health, right? If I want to state of health is around 80%, how do you calculate the 80%? Right? If I take the current capacity in the numerator divided by rated capacity, the current capacity would be around 4H, for example, 4H. Rated capacity when you bought the batteries, right? When you bought the batteries for the new time, the capacity of the battery is around 5H. Okay. After 1 year, the current has been reduced. It has come to the level of 4H, around say 4H, isn't it? So then you can say there is a decrease in the current. There is a decrease in the there is a decrease in the ampere hour, isn't it? So if you take the 4 by 5, right? If you take in the numerator 4 H divided by 5H, right? 4H divided by 5H. So 4H divided by 5H, what it will tell actually? H will get cancelled 4 by 5 into 100. So it comes to be around 80%. That is 0.8 into 100 is 80%, right? So SOH now it is 80%. So that is how you calculate the SOH. Now what is the definitions of SOH actually here? SOH is a parameter that is used to indicate the overall condition and aging level of the EV battery when you compare with the new one. Right. Then what are the parameters you have to consider to find out the SOH? What are the parameters are required so that it is going to make you to understand the very clearly about the SOH. All right. So let us see how this SOH will matters a lot in the especially the EV. Right. So if you see the fundamentals of this formula, as I given the fundamental formula for SOH, a percentage is equal to capacity current capacity to the rated capacity in the Android, right? What is the current capacity? Present available battery capacity. And what is rated capacity? Capacity when the battery was new. So as I given the example, that is the battery was new, it is 5 years, and we used that is when we after using of 1 year, the current capacity would have been reduced to 4 years. Right? If we multiply with 100, 4 by 500, it will use 80% of the SOH, isn't it? So now I just want to explain very clearly that if you take the example of the Tata Nexon EV, right? So if you say about the after 3 years, after 5 years, after 10 years, right, on the end of the life. So what is the aging and what is the rated capacity and what is the current capacity that would be there in the future? It is for the Tata Nexon of the some company. All right. So if you talk about the new, right, when you bought the new for the first time, no, for the electric vehicle, so it is may around for it around 30.2. Okay, 30.2 kWh. Okay, the current capacity around is 30.2 kWh. Okay, so after 3 years, so you have been using the car for 3 years. Okay, so the current is to be around rated capacity around 30.2 kWh. Right, that is rated capacity. Rated capacity will remain same. You see, the rated capacity is almost same. All right. Then, if you see, talk about the current capacity after 3 years, it is reduced to be around 25.7 kWh. Okay, so now you can calculate, right? Now you can calculate by 25.7 divided by 30.2. So that in multiply with 100, it will give the actual your SOH, isn't it? So that is what you can calculate the 20.5 divided by 30. So if we multiply with that one, it is to comes to around 83 point something percentage. Okay, so that is how you have to calculate the your state of health of the batteries, right? And if you see the end of the life, for example, in end of the life, from 27.7, right, that is the current capacity. Then the current capacity was, comes to be around up to 4 or 5 years. We can see the end of the life, right? It is 24.1. So, okay, if you divide by 24.1 divided by 30.2, so what is the value? 24.1 divided by 30 point, if you say 30 point, almost 30.2. Okay, 30.2. So into multiply with 100, so this comes to around 79.80. That would be the SOH for the end of the life. All right, so this is how you have to calculate the your SOH. All right, so SOH is also matters a lot. So where it is taking the most of the time to understand the concept, because when you go for the calculation you'll understand what is the SOH, how it can be represented. All right, so next we'll see by the AI trends, right, how with the different methods, how this AI is going to make the see the precisions of the towards the different techniques. All right. So LSTM is nothing but the long short term memory. All right. It is a long short term memory. So where we just think about the we are talking about the GNN also. We are thinking about the long and short term memory. So where it is going to tells about the life cycle of the numbers, right? And also it will tells about the what is actually the SH. All right. So let us see by this graph versus the life cycle, the life number. Okay, this is the life number versus your actual SOH. Okay, this is the SOH percentage. In the y-axis, you can see there is 100, 80, 60, 40, 20, and 0. These are the SOH in terms of percentage in the y-axis. In the x-axis, we have the cycles. That is the number of cycles. Okay? Or you can see the cycle number. All right. So actual SOH is for measuring this to be around. If you say by the lab measurement, if you say the true capacity which is with respect to the ground, isn't it? With respect to the ground truth. If you say there is a, we can say there is key observations. It was started at the 100%, then dropped down to 70% at 1,000 cycles. All right, at 1,000 cycles, if you see there is 1,000 cycle has been crossed, there is 1,000 cycle has been crossed. You can see this graph, right? And initially it was 100%. All right, then it was slowly. It was when the cycle was increasing, what is happening to the SOH? It is also decreasing. All right, means the percentage of SOH is also decreasing to the 60%. So this is how it has been calculated, right? If you see the GNN based methods, all right, if the GNN based method, this is a group neural network method, based methods, okay. So there also we are thinking about the AI predictions using the GNN. All right. So GNN plus your self attention of that techniques. So where we are going to observe the most of the things that is gets overlap of the error in a tiny every 1,000 cycles, right? So that is what the GNN method will give us a very the crucial the values, right? When you go for the other method, it's called traditional methods, right? In the traditional method also, you can see you can take the old model based that is the Coulomb counting methods. Already you can take the Coulomb counting method to determine the your SOH as well as the number of cycles. From there also you can see how many cycles can be taken, and also diverges after the 400 cycles for prediction for SOH it is 60%. Then may give around the 70%, right? For the Coulomb counting method, that is the old one model old method. All right. So this is how the visualization you can see in the graphical method of the LSTM and the GNN method. Similarly, we have the RMSC also, right? We have to think about the, as I told about the RMSC, where the root mean square error of the value should be very, very less than 1%, right? So that is what you have to determine the, end of the life of the batteries, right? So based on the life cycle also. All right. So here the LSTM methods, if we talk about the GR methods, right? If we talk about the GNN methods, if you see the RMSE value, right? So RMSE value for the LSTM, right? If it is around about 3 days or 3.8%, correct? For a GRU, if you see the GRU, the percentage around 3.2%, comes to be around RMSE value of around 3%. If you use this method, right, the GNN method, it is coming to be around a 1.9 percentage. So if you think about the physical guide, the physical guided GNN method, right? The physical guided GNN method, it comes to be around zero point 0.9, right? So what is actually meaning of this? When I told about, sir, please told about the for the LST method, it is a 3.8 percentage error. What does it mean actually? That is, it says that the real of SH was 80%. Okay, it was 80% when talk about this respect because it was 80%. Okay, so then the prediction may be around of 81.2 to 88.8. That is the meaning of it. Okay, means that there is a small error. Means we are making the prediction of the lives. We are just thinking the prediction of the life, right? It is thinking the what is actually the prediction of the life. So how the life can be predicted, right? In terms of error. So you have said the SH is around 80%, right? As you told about it is 80%, right? It's the real SH is 80% for the LST method. You can see LST method the life is around 80%. Okay. So here LST method the life is around 80%. Then what is the RMS value? RMSE value. Actual RMSE value may comes to be around less than 1%. Okay, if it is 81.2 to say around it is 88.8%. So that is actually the RMSE value, right? So it is also used. These techniques are also used in various of EV basis and AI BMS. That is various your electric vehicles and also the artificial intelligence battery management system. Also, this is the LSM technique is have been adopted. Okay, it's been used. Okay. So when you talk about the another one, right, which is another one, we have the GRU. Okay, we have the GRU. So in this GRU, the RMS value is around to be 3.2%. Okay, you see RMS value is how much it is? 3.2%. Isn't it? It is a 3.2%. Okay. So now if you see about the SOH, so which is SOH to be comes to be around slightly better than LSTM, right? It is slightly better than LSTM method, right? And the more faster also. So more faster also, if you see it is comes to around 80, 80, like around comes to be around 80%, right? So these are also used in the earlier days of the mid EV. Okay, it was an old method, right? It was used in the mid of electric vehicles. So all right. So when you talk about the another, right, GNN, right? So GNN, graphical neural network, right? So graphical neural network. So what it will tell actually in the graphical neural network? When you talk about the graphical neural network, what it will tell exactly for us? So when you talk about the graphical neural network, you can see what is the RMS value for that. RMS value, as I told, it is to be comes to be around 1.9%. Okay, 1.9% for the GNM, 1.9 GNM. Right? Now the real of S is 85%. Okay, now you say the real S was around 85%. Just we are just taking the example. Okay, so you can make the prediction of with the help of the RMSC that I told about the less than 1%, and it comes to around 83.1 to 86.9 percentage, which matches with your RMSE square values, right? So that's to be around a 0.994, 0.9947 values. All right. So these are used in the premium of electric vehicles during the most of the cases. All right. So finally, we have called it physically guided GNN, right? Physically guided GNN. What is the RMSE value here? RMSE value is 0.9%. Okay, we can see RMSE value is 0.9%. Okay. So now if we say that for SOH for this is around 85%, right? So we are just expecting to have the RMSE value in the with respect to the RMSE value, the error should be less than 1%. it comes to be around 84.1% to 85.9% after making the analysis. All right. So these also used in most of the cutting edge electric vehicle in the current areas, right? In the 2026 of EV research. So most of they are doing this in the EV research in cutting edge AI. All right, for the EV research. So this is how the visualization of the SOH distribution can be understandable from this graph. Okay. So I hope it is very clear to you. This is the most interesting and the understandable the pattern of your SOH versus the number of cycles and also the estimation method, right? We have seen the estimation method of LSTM, we have seen the estimation method of GRE, we have seen the estimation method of GNN, we have seen the estimation of physically guided GNN also, right? With respect to your RMSE, right? So that is how we are just making the prediction of the SOH for the different estimation methods. All right. I hope it is clear to you this concept. All right. So next we'll see why we have to do monitor for the EV for the state of health, right? The one question I just want one question is why you have to go for the monitoring the EV? Is there any necessity to go for that? Do you have any necessity that you have to go for monitor every time you have to go for monitoring the EV? All right. Anybody can tell why? What is the purpose of going for the monitoring the EV all the times? All right. So let us see why do you monitor your EV batteries for the state of health, right? So the necessary is that you have to monitor for 24 hours, right? Every second, every minute, you have to get the data, so you have to check your data and you upload the data in the clouds. So we'll see the one best example, right? Here, the battery in the EV is compared to the vital organ that needs a regular checkup to stay healthy, right? So you can say the battery is the, as I told, battery is the heart of the electric vehicle, correct? Battery is the heart of the electric vehicle, right? It is also the vital organs. So when you talk about this vital organ, so your in the human body, right? In the human body, the heart is a which is most important organ for the human being, right? Which can pump the blood from the brain to your feet also, right? This circulation will happen. It is controlling your entire body with respect to your blood circulation. Solid. So like that, battery is also heart of the electric vehicle, right? Without the batteries, you cannot run the electric vehicles, right? Battery is also giving energy to your most of the motors to drive the motors, all it and motor for controlling the circuits and the connectors. Everywhere it is giving the supply from the battery, right? That's why the battery is the heart of the electric vehicle. As like it is pumping the blood from the your heart to the every nervous system of your brain as well as the part of your organ, right? Similarly, like that, the battery is also the most plays a vital role in the EV. Okay, that's a battery. We have to say that battery is the heart of the electric vehicle, right? Battery in the EV is compared to the most of the very vital means it is very important organ, right? If you see the vital means it is a very important organ that needs to be made a regular checkup. If you want to stay healthy, if you want to stay healthy for the battery, right, you have to go for the regular checkup. All else what will happen? You cannot if you don't monitor the health condition, no, it will become a very difficult to uh, understand why what is happening with the batteries. All right. So that's why you have to check about the battery health condition most of the times. All right. So that will help us to keep the battery to be more healthy also. All right. If you see the most of the EVs are equipped with the battery management system, right? If you see nowadays the most of the vehicles, right? It may be a four wheelers or two wheelers. They may have the what is it? They may have the BMS techniques, right? That will monitor your battery conditions continuously, right? So that's why we have to see the EVs we have to monitor the various parameters such as current, voltage, temperature. So these are the things you have to monitor continuously so that if you take this data and make the analysis with of your machine learning, so after your taking this data into the clouds, you will try to understand the various factors. All right. So that's why you have to monitor your electric vehicles batteries. All right. So if you see there is a one thing is that we have to understand why the regular checkup is required. If you don't make the regular checkup, what will happen? There is a chances of capacity feed. I explained in the previous sessions. There is chances of the power feed. There is chances of the safety also, right? So these are the three factors you have to remember, right? So as we discussed in the quantifying conditions, you can see there is a quantifying condition over here, right? Uh, yeah, here only. This is the quantifying condition. That's why you have to make the predictions. That's why you have to make the monitoring the batteries at all the times, right? If you have to go for the quantifying all these conditions, right? So that's why this was the first benefit of the SH in our early the very most first thing we have to understand how this the EVs of why you have to go for a monitoring. Right? If you don't monitor, what will happen? Capacity failure will occur. All right, and the power fade will occur, and also the safety. You have to think about the safety is also sometimes. So that is also very very important. All right. So when you talk about the capacity failure, right? So if you see there is a loss of 2 to 3% per year. Okay, if you see the capacity failure for 2 to 3% per year, even there is a aging of the cells, right? If the aging of the cells also there is chances, right? That's why you have to monitor. So if you monitor also, still we are observing that there is a 2 to 3% of capacity fade has been happening for every year. So what is the action you have taken, right? Yeah, what action you have taken? You are not taking any action. No. So that's why you have to monitor your EV batteries. Solid. So that is a very, very most important thing. So if we don't monitor now, so the things will be happen very difficulties in a very difficult condition. All right, to stay that to make the battery to be stay healthy, then we have to go for the monitor your electric vehicle batteries also. All right, so that is a very important vital organ for to drive your electric vehicles. If you don't monitor, the health checkup is not happen. Obviously, if you don't, for example, if you have a fall sick, right, yeah, you will go for the checkup for to with your doctor, isn't it? So they'll give various prescriptions and they will tell you to take these tablets and all that. So that's why we also have to do the same thing for the batteries, right? Because we are a battery engineers, right? We are a EV engineers. We have to think about the each various parameter, what is happening inside the cells, right? That is what we have to think, right? If you monitor each and every parameter, no, the things will become very easier to make to stay very healthy for the batteries. Solid. So next is we have to see about the how this most of the EVs has been equipped with the battery management system. Right? Most of the if you see most of the electric vehicles, right, they have been incorporated with the BMS systems, right? Because BMS will do its job. It will monitor your health conditions continuously. Right? It will try to give you the various parameters also, right? It will try to measure. Let us see what the BMS blocks will do here. What the job of the BMS block? If the BMS block ಏನು ಮಾಡಿದ್ದಾರೆ ನೀವು ಇವಿದಲ್ಲಿ incorporate ಮಾಡಿದ್ದಾರೆ ಅನ್ಕೊಳ್ಳಿ ಏನು monitor ಮಾಡುತ್ತಂಗಿದ್ರೆ what is going to it is going to monitor what is going to monitor you have to see what is the measurement it is taking let us see what is measurement it is going to take that is we studied in the previous right so that is the voltage it will take the current it will take the temperature every 100 milliseconds every 100 milliseconds it will they collect the data right from each cell not from the battery not from the module or a pack. Okay, it will take the data from the each cells. Okay, that is what I'm talking. Alright, so it will try to take the data from the each cell because for the measurement purpose. Okay, so that is what it has to think about how the once you take the data, so you can think about the LSTM techniques. Right, in LSTM techniques, you will make it to understand the concept very clearly if you collect the data. Okay, or else you can go for the GNN also, right? All right. So other thing is that you have to see about the other state of estimations, right? What is state of estimation it will do? To check the physical guide for your GNN on MCU, right? GNN using GNN methods. So we'll try to monitor the estimation techniques, right? So what is the value of RMS if it is less than 1% or what is the SOH? How fast it will be there? That is what it will try to check. If you see the another one, there is a controlling techniques, right? What is going to control the lithium charge, right? The lithium charge in the current. If the SOH is around less, if it is less than 85%, right? So what it is going to take the what method you are going to implement for the which you can link with the AI, right? You have to maximize the lifespan of the lifespan. This is what I'm talking about here, isn't it? I told about all the lifespan also. Right? This is how you have to maximize the lifespan. So when you take about the controlling, right, you have to see what is the limiting charge that is happening for the energy delivery, right? Limiting charge for the SOH is less than 85%, right? So what is the methods you have been applied for the AI, right? We have to see think about the maximum life techniques, right? Where you can go for the benefiting of the maximum life using the AI techniques. So this is the reason, right? That is what you have to think about the battery management system. That is what it is doing. The most of the it is trying to connect with the all the various parameters and measuring the various technique, various parameters also, right? It will use the accuracy for the EVs to run the vehicle in a healthy and nominal conditions, right? So let us see how it is going to be happen. In the think about when you talk about the various factors such as the new cells and the aged cells, right? With respect to the resistance, right? When you talk about it with respect to the resistance, if you see impedance and spectroscopy measure the internal distance of the different frequency to act as a battery wear. Okay, so here what actually the internal resistance it will tell you. Internal resistance of the battery is nothing but we have the EMF, isn't it? In the EMF you have the internal resistance. Okay, when you talk about the internal resistance of the battery, so what does it mean actually internal resistance of the battery? Right, if the resistance increases, what will happen to the current? The current will decrease. Yes or not? If resistance increases, no, so obviously the current will decrease. There is no charge in the batteries, correct? We don't find any charges in the batteries. So that's why we have to think how the internal resistance will make a lot of impact in the electric vehicle batteries, correct? So if the resistance is going to be increased, obviously the charging, the current will also get reduced. There might be the rise in the temperature. So that's why if we have to think about if you take about the age cells, right? If the age cells is around 50 milliohm, isn't it? So around for 50 milliohm, it is 100 SOH. After the age cells, sorry, you are taking for the new cells, that is the value for R internal, that is the internal resistance of the battery is around the 50 milliohm, okay? So that gives you 100% of base voltage in the initial stage. After age stage, the same cell has got age now, okay? So that's what I'm telling about the aged cells. So aged cells, when it is comes to be around 90 milliohm, means the resistance is already increased from the 50 to 90 milliohms. Then the SOH will also decrease. That is maybe comes to be around 70% of SOH. So that is how the internal resistance will make a lot of impact in the EV batteries for the state of health conditions. So that's why you have to see the various methods how to practically we can think about the to think about the RMSE values for the making this battery to be more having more SH, right? So use the AI methods for the using AI only methods. Every time you can drive the real time data. All right. Think about the accuracy, that is the RMSE values which is less than 1%. Most of the EVs that have been used, such as in the Tesla also it has been used, and also with small injection of various parameters, right? You have to see how this will play important roles in the internal distance. All right. So these are one of the examples, right? Then we think about the with respect to the various factors. Right. When you talk about the full charge, full discharge of test, right? You can see how the accuracy will happen, right? Whether it is 1% or 0.1%, we have to see how it is a grid. When you talk about the power grid, right? We have to think about the life cycle, the waste of the life cycle. Is it one or two or 100 or 2000? What is happening? We have to see. If we see the other method, right? That is the cloud EI estimation, right? So it will for accuracy for the RMC would be around 1.5% if you use the cloud AI techniques, right? So these are various techniques you can go for analysis for your SH also, right? So it also makes us to think about the more on the BMS, right? So all these techniques is very important for your to monitor your EV conditions, right? Now, if you see the real-time updates on the battery cells are now possible to drive thanks to advanced measurement techniques. Right? As I told about the real-time update, right? You have taken the real-time update of measuring voltage, temperature, current. These are the various parameters you have taken, isn't it? So how this will make a lot of impact on the battery health condition, right? While driving, during the charging and discharging, every time it is going to take all the data. Every time it is going to take all the data and fetching the data from the battery cells. We are just connecting a certain kind of sensor to measure that to access the data from the on the real time. Right? It will help us for charging and discharging purpose, and also the finding the remaining life of the batteries also, or finding the SOH also, right? So we have to think for the thanks. We should make a thanks for the advanced measurement technique, right? Which we are studying in the previous sessions. All right. So next, when you talk about the capacity measurement, what is capacity measurement? How much of capacity is remaining in the batteries, right? The actual capacity to the used capacity. That is what the how much of capacity is remaining, and also the actual capacity. So that's why you have to think about more on the how it is happening on the various types of the capacities, isn't it? So we have to think more on the how the charging and discharging is going to be happen. All right. So these are various techniques we have to understand actually how the charging and discharging is happening. All right. Okay. So we have the capacity measurement as I told about the how we are going to measure the various parameters, right? The current voltage and the storage capacity with respect to the origin capacity. That will indicate the aging factor also. All right. So here, if you see the capacity measurement, right? That is what we have to see how much of charge has been stored and how much of energy has been retained, the remaining energy. That is what you have to think about the SOH fact, right? That is the capacity measurement. Will tell us about the. It will compare about the current energy, that is the storage ability part to the original capacity, right? That is what, if you see the battery capacity is around of 50 years, okay? Then the actual rated capacity is 50 years, and the capacity that is measured during up to 2 to 3 years, it may be around of 20 years, right? So 20 by 50 into 100, if you multiply, that will give the actual value of the SOH. All right. Next, and also it will indicate the aging also, aging factor. If the SOH get reduced, the aging will also can be reduced for the battery life. All right. So now we have the various techniques, right? That is the one is the incremental capacity analysis, and also we have the differential voltage analysis. We have the track voltage and the capacity change during the charging and the discharging, right? So these are the various methods where you have to think about the how these real-time updates can be happen while driving also, right? So and also you have to think about the advanced incremental technique methods. That is ESI plus EI. So in the advanced incremental technique methods, you can go for the ESI plus artificial intelligence, right? And also, if you think about the capacity measurement, if you think about the in the capacity measurement, you should go for the SOH techniques. That is, you have to measure the using the SOH formula. You can identify the SOH in the BMS. All right. So that is what I told you. No, if you take the example of any EV companies, the battery is around 30.2 kWh, right? Right. When you bought the new car, after 3 years, if the BMS measures at 25.7 kWh, okay, then what is the value of SOH? Then it is coming to around 85%. It means that there is aging is happening. So that is how you are going to measure the capacity. All right. If we talk about the incremental capacity analysis, right? So that is what you have to think about the BMS plot of dq by dV. That is a change in charge to the change in voltage versus the voltage if it identify. No? So it will give the curve shift of the battery's age, and also it will tell us about the battery health also. This will do by the AI. AI will track the peak shift from the estimation of the SOH. All right. So when you think about the capacity changes during the charging and discharging, right? So these are the various things you have to see how the batteries can give a life for the with respect to these data, how the battery can give the life. All right. So these are the various techniques you have to monitor each and every time. All right. So next we have to monitor the internal battery modules, right? Uses the which can use the sensor and various algorithms to estimate the parameter like the lithium level and prediction of the lifespan also. Right. So think about the battery health condition, right? How it is going to charge, how it is going to discharge, and we have to see the temperature. What is the temperature during the time, and what is the current it is drawing, and what is the voltage it is drawing. So for that, you require the sensor. The sensor is also very very important. The sensor is also very very important. So we have to think about the by using the various sensors how the sensors can be utilized to take the data from the measuring instruments and also from the parameter of the battery cells. Alright, it will help us to give the various things to make us to understand the life cycle. The prediction of the life cycle is also can be possible if we collect the data from the sensor and try to implement using the algorithm, right? It will check about the internal batteries, right? It will take the internal batteries of data by using the sensors and also algorithm. It will estimate the your prediction life of the batteries. All right. So let us see what are the components are required to use the sensor. For using sensor, you need to collect the voltage, current, and temperature from the sensor of each cells, right? So and also try to have the internal model in the BMS. So every input data has to be collected every 100 milliseconds, right? And then you think about the one block of each in the BMS architecture. Okay, so if you take about the algorithm, right, you have to read the battery data such as the chemical aging, what are the chemical aging it is happening in the inside of the cells, right? And what is the model we are going to use in the BMS? You can go for the GNN, that is the graphical neural network also you can use, and also you can use the physical guided graphical neural network also you can use the Kalman filter also. From this, we can make the AI can be we can predict the RMS value is less than 1%. All right. So if you think about the other parameters, right? Think about the losses in the lithium, right? The real lithium losses, how much it is happening, and also SIA growth also, right? That is a use a model for estimation such as active real and also the that is what the R internal of the capacities of the resistance of the batteries into the resistance of the battery, right? So these are the various techniques you should algorithm. Please, we have to implement on the various components to understand the battery health conditions. All right. So these are the most of the things. All right. So you have to go for understanding the various techniques. Based on this, we can see how the battery life can be given. All right. And it will try to understand the charging data and especially the voltage behavior during the constant time. It will also give the current phases that will provide the clue for the battery degradation also, right? So every time it tells about the your right, it will tells about the connecting the sensors. It will tells about the new battery current cells. If it is around 80%, if SOC is around 80%, right? And old battery current capacity is around 65%. The SOC time loss will be around comes to be around the SOH loss also, right? Sometimes it is more connecting all the sensors should be connected, right? To collect the your actual current data, right? And to apply using the algorithm of GNN techniques for finding the SOH. We can take the data into the clouds and make the predictions of the batteries or if it dies in the 2 to 3 years. Right? That is how we can make the prediction of the batteries of the lifespan. All right. Now, if you talk about the machine learning, right? Machine learning will try to analyze most of the things, right? It will teach you the various patterns. If you give the historical data, right? If you give historical data, it will understand how much of data is required for the analysis. Right. So BMS will try to calculate the actual of conditions of the batteries by collecting the various parameters, right? It will try to see what is happening inside the batteries, right? With the help of the BMS, right? It will check about the internal battery models, and it will try to see the various sensors which can be sense the various parameters such as voltage, current, temperature, right? And the sample of each cell every 100 milliseconds it will take the data. So this is where we can take the measuring the data that can be given to the clouds for the analysis purpose, right? And now we have to apply the AI algorithm. Nothing but the that is the brain, AI brain, right? Where the model uses the GNN or the physical guided GNN. Also, you can use the Kalman filter to process your sensor data, right? It does gives the RMC value which is less than 1%, right? So these are the various methods you have to see, and also you have to predict the lifespan, right? That is the remaining life of the batteries you have to see, and also you have to see the charging and discharging. We have to see the various patterns and the voltage behavior. Solid. So when you talk about the monitoring the internal resistance, that is the internal resistance of the battery and the temperature will help us to easing the factor of the cells and also helps prevent the safety issues. All right. So these to be combined methods where it can optimize the charging, scheduling, maintenance, and also repurposing the used batteries. All right. So that is what the regular battery health checkup is very very important to ensure the vehicle remaining reliable life of the batteries, right? And that can be used for the ready to use. Right. So here you can see it is very clear that we have to understand the concept of the SOH. All right. So we'll see how this SOH can be studied, right, with the help of the various graphical methods. Right. We have to think about more on the in the previous slide I told. We have to think about the internal distance, right? The internal distance also, internal distance and impedance also. We have to think about the batteries. So these are the two factors. We'll try to see how this can be analyzed with the help of the graph. Now you see there is a graph where we can make the prediction of the SOH estimation, right? So in the y-axis, you have the battery capacity in terms of ampere hour, right? It is ampere EH, ampere hour, right? In the y-axis, you have the number of cycles, in the battery cycle, right? So that is 200, 400, 600, 800. So now you see, you have here it is a zero, okay, almost zero, point 0, comma 0 points, okay. So when you bought a new battery, right, it is around 48. Okay, you can please note down. When you have a battery of 48, the life cycle was 0. Okay, means you are not used at once also you are not used. Okay, for 48, the life cycle is 0. Okay, so after usage, right, when you fit the battery into the electric vehicle, right, so when you start driving the vehicle, the battery used to consume the energy density from the batteries, okay, and the power density from the battery, where it will try to think about the how the number of cycle charging and discharging will happen. So based on with that respect to in the x-axis, you'll see the cycles, the 200, 400, 600, 800 cycles we can see. All right. So here you can see there is a battery capacity. So when you bought for the first time, no, it is around 48, right? The cycle was 0. So as soon you use it, when 200 cycle is 200 cycle is crossed, so what will happen? The EH will start gradually it will decrease. Okay, it will gradually it will decrease. I can show in the next slides. Okay, you can see here when you bought for the 40 for the first time it was 48, right? The zero cycle was a number of cycle was 0. Okay, after usage, no, you cross the 200 cycles. Okay, you see there you have been crossed the 200 cycle. So what is happening here when you cross the 200 cycle? The AH is getting reduced. Ethanol, you can say there is a AH is getting reduced over here, right? So that is from 40 to 37 AH, correct? From 40 to 37 AH, the AH has been reduced. So when you talk about again when you, the 400 cycle is completed, right? When the 400 cycle is complete, what will happen to the battery AH? Again it is getting reduced. Again it has been reduced. Gradually it is getting it is reduced. Okay. When you talk about the 600 cycles, okay, when you talk 600 cycle, the AH is again it is reduced. When you come to the 800 cycle, 1000, then it will come to 31, 25, 10. So that is how the life cycle will also end, right? The end of the battery of the life will get ended. So that is how you can see the estimation percentage. Okay. Now you see you have to calculate the percentage of SOH. Right? How do you calculate the percentage of SOH? For example, 37, right? 37 is the your actual battery capacity, right? So 48 is the battery capacity, and remaining capacity in the battery is 37 Ah. Okay, if you see the calculation of the 37, so divided by 40. So how much it will give? 92.5%, correct? Similarly, you can calculate for the 35. Okay, 35 divided by 40 into 100. It means it is given the SOH is around 87.5 percentage. Okay. Similarly, you can calculate for the 33 divided by 40. 33 is the actual actual capacity energy remaining capacity. Okay, and the battery capacity is to be around 48. Okay, that's why I am taking the 33 divided by 40 into 100. So this comes to around 82.5 percentage. Okay, like this you can calculate for the 31 also. 31 divided by 40 into 40 into 100. 31 divided by 40 into 100. It is 77.5 percentage. Okay. So this is what actually you are going to calculate the SOH. So next thing is that you have to understand with the impedance. As I told about talking about the ESR, right? That is the ESR has to be comes to be around in terms of milliampere. Right? We'll take this graph to understand the very clearly about the battery capacity along with the life cycle of the number of cycles of the battery. In the x-axis, in the y-axis, we are taking the battery capacities. Okay. Now we'll see in the y-axis we will also consider the battery capacity which is parallel with your equivalent series resistance, that is ESR, equivalent series resistance. Okay, this is the EMF of the battery, this is the internal resistance of the batteries. Okay, which in terms of the milliohms. So now let us consider internal resistance will also make a lot of impact as already told, right? If the internal resistance get increases, right? When you bought for the first time, the internal resistance was I told how much it is 50 milliohm. Okay, after 1 or 2 years or 3 years or 5 years, again the internal resistance is comes to around 90 milliohm. I mean there is a drastic change in the internal resistance. So how it will make the impact on the SOH also, right? And because of the rise in the temperature, what will happen due to the rise in the temperature? And also, if the resistance increases, the current will also will drop. That is why the equation I is equal to V by R. Okay. If R increases, I will also decrease. Correct. Now let us see in the y-axis. We have taken the equivalent series resistance. That is ESR, right? ESR in terms of milliohm. Correct. In terms of milliohm. So we have been taking the y-axis which is parallel to the your battery capacity, correct? With respect to the battery capacity, the ESR has been taken into consideration. All right. So now if you see equivalent series resistance, that is ESR in terms of the milliohm. All right. So now initially when you bought for the first time, it is here. Let us take the example of this only. It is a 20 milliohm, right? So after 5 or 6 years, okay, what will happen? The ESR of this milliohm will try to increase from 40 to 60. Okay, 40 to 16. There is a drastic change from the 40 to 16. There is 40 difference. Okay, 40 million difference is a difference. So what will happen during the time if resistance increases in the internal battery, so the current will also gradually decrease. Correct. So that's why you can see there is a decrease in the EH. There is an increase in the milliampere. But you can see from for 20 to it initially it was 20, isn't it? Initially it was 20. Then you can see there is a gradually increase in the milliohm resistance. Okay, so that's why the age is also decreasing, and also there is increasing in the life cycle. Right? By this also you can make the prediction of the SOH. That is, you can determine the state of health conditions of the batteries with the help of the impedance also. Right? This is just because of the rise in the temperature. Sometimes when you charge the battery, there is a rise in the temperature. Sometimes the bad cells in the battery module, right? So during the driving conditions, during discharging also the temperature will also rise, and the internal distance also makes a lot of impact on the state of health also. All right. So this is the one example we have taken to make you to understand that very clearly. All right. So I hope it is clear to you. The battery of SOH with respect to the impedance, right? With respect to impedance, that is how the batteries is going making a lot of impact, right? With respect to the internal distance. So next, let us see how what are the ways to estimate the SOH? What are the different ways? Can anybody tell me what are the different ways of estimation of SOH? Okay, all right. So there are different ways of to estimate the SOGs. One is to measure the capacity, right? You have to measure the capacity of the battery. We already discussed about this formula, right? That is measured capacity to the beginning of the life's capacity. Right? The measured capacity is nothing but the after 1 or 2 years it has been decreased to. See here you have the 40 H in the beginning of the life, in the beginning stage, right? After 1 or 2 years, 200 cycle has crossed, it comes to 37 H. Then 400 cycle has crossed, it comes to around 35 H. Okay. So like this, you can calculate. There is one way to calculate the battery switch. Okay, measured capacity is to be around 31, and beginning of the life it was around 40 right? So if you take the 31 divided by 40 right? Right, it comes to be around how much? 77.5 percentage, correct? 77.5% is the SOH technique, SOH waste, SOH values. Correct. By this, you can calculate the various forms of the SOH to to understandable. So right. So with the help of this, you can understand the what is the other methods, right? What is the different other methods? We can see how to calculate the SOH or the D by using the different methods. Okay, this is one method. Other method we'll see with respect to the other parameters, right? The internal resistance, right? As I talk about internal resistance is also making a lot of impact, isn't it? So internal distance will also measuring the internal distance will also gives the other methods to life for the batteries. Okay, because of the rise in temperature. So if we think about the beginning life is to be around 40 H only, right? So as the temperature of the resistance will increase, so what will happen? the resistance of the batteries if increases, the internal resistance of the batteries in the cells increases. So that data has to be calculated, right? The data has to be given to the clouds and it will give the corresponding SOH values, right? So that is you have to think about the machine's internal resistance, right? So you have to calculate the actual EH when you got for the first day, okay? Then estimate using your SOC and also the charge time using the GNN method also, right? It will give after 3 years, right? If it is around 40 for example, you taken for the 30 after 4 or 5 years, 3 years, it will give the 25.7 kWh. So that is how it calculate the age with respect to the resistance, right? If the resistance also increases, what will happen to the batteries? The battery life also will increase, right? So that is what when you talk about the internal batteries, right? So that is if you talk about the internal resistance of the batteries, right? So how does it makes an impact on the BMS, right? So 50 milliohm, that is for the when you take this data for the testing, right? After 1 or after 1 or 2 years, right, the resistance has been increased from 50 to 90. So what will happen to the Q value? The Q value also will be reduced from the each cell when you take from the data from the each cells. So that is how the estimation can be happen, right? So these are the two ways, right? It also tells about the how the SH can be calculated, right, by the two different methods. That is one with the measuring the capacity, other is the measuring the internal resistance. Okay, so this will completes your SO state of health, right? We already studied the SOH in the very SOC in the previous sessions. In this session, we have studied the SOH. All right. Now we'll study the thermal management of electric vehicles for the battery systems. Alright, this is another topic where we have in our syllabus. We have to think about the thermal management of the electric vehicle of the batteries. Okay, so what is the thermal management? Thermal is nothing but heat, isn't it? Now heat is it possible to get the heat in the batteries? Yes. During the charging and discharging, there is a rise in temperature will happen. I have shown in the previous session the data, right? The data sheets where for the different current and temperature, for different current and voltage value, we have the temperature is to be maintained around 25 to 26 degrees centigrade. Right? That is what you have to maintain. I have taken the n number of data for the machines to give the data to be fed to the machine learning, where the machine is to learn the by itself under supervised learning. It used to give the it used to give a lot of various data where you can see how the temperature has been maintained constantly for the various voltage and current, rise in the voltage and current, in the charging and the discharging time. Okay. So now the thermal management for the electric vehicle. Well, we'll understand what is the BTMS. What is the BTMS? Battery Thermal Management System. All right. So battery thermal management system. Okay. So now BTMS will tell us about the battery thermal management system. What it will tell? It is subsystem in electric vehicle. Means it is a part of the BMS. Correct? It is a part of the BMS. That's why it is a subsystem. It is a part of the BMS. That's why it is a subsystem in an electric vehicle. So that controls and maintains the temperature of the battery pack within a safe, optimal operating range to ensure the efficient performance, safety and reliability also, right? So you have to think about more on the battery cells also, right? So the thermal management for the electric vehicle is also very, very important. So we have to see how the battery safety can be matters a lot for the not to get the degradation to increase the life of the batteries also. All right. Let us say the battery. What should be the battery temperature then? So you can say that, sir, what is the temperature of the battery that we have to maintain? You can maintain from the 15 degree to 35 degrees centigrade always for the batteries. All right. So you can go for this nominal temperature. Beyond that, it should not go, and beyond the colding should also not happen, right? And below that temperature, it should not happen. We should not increase the temperature value of more than 45 to 50 degrees centigrade. You can go beyond that. Also, you can go for a negative temperature also. So that will make a very critical factor for the BTMS. Solid. So that's why I have to think about the battery management system, right? During the normal conditions, also during the DC fast charging, also, and also during the driving, also think about the temperature. Always you have to think about the temperature, right? So if you go for the right, so if you think about the batteries, right, the batteries conditions, what is happening in the battery conditions, the temperature coming less than 10 degrees. What BMS has to take the action. Now, the BMS here, when you're measuring temperature, okay, suddenly the temperature falls to the minus 10 degrees. So, what you'll do, right? So, you have to turn on the PTC heaters. so that the temperature will start rising in the battery. It will come to the actual temperature, right? The that is the battery heater you have to use, right? So especially in the most of the vehicles, that is Nexon and Norvis or PVs has been there including these techniques. All right. So that is what given the one example to make it to understand. All right. So BMS is also plays important role to safeguard the batteries of the light bulbs. All right. So it will not catch the fire. It will not have any sensation in the burning. All right. So the BMS will plays important role in the BTMS. All right. So BMS is like a brain, right? BMS is like a brain, and BTMS is like just like hands. So the example is very clear, right? BMS is like a brain, and BTMS is like a hand. All right. So this is one thing, so you can understand very clearly, right? Again, the differences of the BMS and the BTMS. Alright, so BMS reads the temperature sensor, right, and decides whether it is too hot or it is too cool, right? And especially in the most of the Tesla car, also we have the BTMS pumps of AC start, and also which is connected to the control blocks in terms of in the electric vehicles, right? So you have to think about the more on the temperature gets rise, so we have to go for the cooling techniques also. We have to go for the when the hot problems occurs. We see what are the hot problems occur. If the temperature is going to be around 65 degrees centigrade, right? What actions you are going to take? So suddenly they should have the power cut, right? They should have the power cut, and till that reaches back to the normal temperature of 40 degrees centigrade, right? So that will prevent the safety issues for your batteries. So that is what you have to think about the hot problems during the when temperature got rise to the maximum values. All right. So during the fast charging also, right? Think about the fast charging, right? How much of temperature is being rise during the DC fast charging, right? So these are will gives a lot of impact on the BTMS. All right. So here you can see now it is very clear that the BTMS is a subsystem. That is a BTMS is like a hand and BMS is like a brain. Okay, in an electric vehicle. So what is the job of the BTMS? It will control and maintain the temperature of the batteries. All right. It will control and maintain the temperature of the battery always. All right. Okay. So it will try to maintain the temperature of the battery pack with a safe and optimal operating range to ensure the efficient performance, safety, reliability, and the long life of the batteries. Okay, you have to think how the batteries can be monitored and what are the different types of temperature ranges we have. If it goes less than the minus 10 degree, what action you have to take, right? So that's why the BMS is incorporated in the electric vehicle. All right. So that there will be safeguard for the heat cells and also operating range can also be improved and also performance will also be very good and the safety will also can happen continuity of the power delivery to the energy delivery to the components for the battery to the motor it can also be happen and it will give a longer for the batteries. All right. So thermal management system, what is the controlling action will take? It will EV batteries generate the heat during the operation. So that we already know it, right? When the EV batteries during the running conditions or during the charging condition, during discharging conditions, all right. So EV will try to generate the heat, right? Especially during the fast charging or during the high power output, right? So during that time, the BMS will work like a liquid or a air cooling system, right? So that's why when during the charging and discharging, the each cells of the body should have the channels, right? Where you can make the cooling effect for the individual cells also, or you can fit the fan for the air cooling, especially in the power grids, right? In the grid. Where you are using the DC storage for in the grid for HVDC in the Kolar, right? So they are using the completely the cooling systems where the battery gets heated up. It has to be cooled, right? To reduce the temperature of the battery so that it will not go for the degradation, right? There is a regular control will be there, the battery temperature, and we have to optimize the performance and the preventing from the overheating. So that's why to go for the cooling techniques. So these are the techniques where you have to go for the either liquid cooling or air cooling. There may be active cooling, there may be passive cooling, or it may be a hybrid cooling. So let's see the different types of the cooling which we have to study in the these sessions. All right. So now this is very important and the crucial factors where the battery get increases the temperature, then you have to go for a different cooling options also. All right. So like I say, these are the different types of estimations we have studied in the previous sessions. Okay, we are discussing about the battery state estimation, right? That is the state of charge, state of health, state of power, state of energy, state of function, right? So these are the various estimation techniques, right? The state of charge usually it, represent the available energy in the batteries as a percentage of its total capacity, right? That is what we discussed in the previous session. That is the state of charge. How the state of charge will matters a lot for the batteries and also state of health condition. It will indicate the overall health and degradation of the status of the battery, right? And when you talk about the state of power, right, it determines the maximum power output or input the battery can safely deliver for the at a given moment, right? And also if we see about the state of energy, right, measure the total usable energy available in the batteries at a given time, right? The state of function. So these represent the overall functional capabilities of the battery considering the multiple operation parameters. All right. So we'll see what is the state of charge for the batteries. We'll see why these are very important, right? We say about the SOP. So SOP, if it is around comes to be why it is more important the SOP, why it is needed, and what is the purpose of SOP for the say state of power, right? If the SOC is 80%, but the battery is five. Battery is -5 degrees, and the SOP limits power to be very less. You can press the accelerator car, it won't respond, right? So that's why you have to think about the state of power, right? It determines the maximum power, right? The maximum power is to be around somehow the SOP is why SOP is needed. I'm just make it understand why SOP is very important, right? Why SOP will take an important role in the these things, right? So it will tell you the how the maximum power can be delivered, right? If the SOC is 80%, but battery is if you see battery is -5 degrees centigrade, right? If the battery is around -5 degrees centigrade, okay, then the SOP will limit the power, right? The SOP will try to limit the power. If you press the accelerator, no, the car won't be responding. So that's why we have to think about the state of power, right? The state of power is important factor. Next, if you see about the state of energy, right? Where the real energy is required, right? If the SOC alone has a less than 50%, I'm just giving the example of SOC alone has a lies in the 50%, right? If SOC lies in the 50%, the SOC on a new versus the old battery if we take, no, plus it with a different kilometer, right? The SOC will correct if the SOC plus SOE plus SOC. When you multiply the SOH and the kWh, so that will define the actual the state of energy, right? So that's why you have to think of the SO energy also, right? And finally, the functioning. All right, the functioning will tell about the represent the overall function of the capabilities of the batteries, considering the multiple operation parameters. So, what are the different multiple operation parameters that is it is going to undertake? That is what we have to think about the state of the function. All right. So let us see the thermodynamic system. The EVs are sustainable alternative to the internal combustion engine vehicles. Right? The lithium-ion batteries are widely used due to the high energy density. The BTM, that is the battery thermodynamic system, are essential for the battery safety, longevity, and the performance. Right? This represents the war BTM strategies and the changes with respect to the future trend also. Okay. In the olden days, we are having the very internal combustion engines before introducing the electric vehicles and hybrid vehicles, right? So the lithium-ion batteries are most of the days now we are using lithium-ion batteries. In future also, we can go for the electric vehicles to start the vehicles for the initial stage, right? The lithium-ion batteries also are widely used due to the high energy density. Right? So that's why the BTMS has a very essential role for the battery safety and longevity and the performance. Right? So BMS will also makes a lot of impact on the BTMS, where the safety is also required for the longevity and the performance. All right. We are going to study the different strategies, challenges, and other future trends also. So why battery thermal management is very critical? Can anybody tell me why it is very important? Okay, all right. The temperature sensitivities, which is to be around 15 to 45 degrees, that is the optimal temperature. Please, you can make a note of it. The battery thermal management system is very, why it is very critical. All right. So you have to think about the lithium-ion batteries, which is operating at the range of 15 to 45 degrees centigrade, right? And next factor is that the thermal runaway risk. There is chances of the rise in the temperature during overheating can lead to the cast fire, and also the sensation of the uh, smell also for the fire, catching the fire, and explosions will also can happen. All right, the next is the lifespan. When you talk about the lifespan of the batteries, there is excess of heat you can isolate the battery aging also, right? So they shouldn't have the overheating of the batteries where it leads to the enormous of heat which is produced in the battery that will try to degrade the battery's life, and also aging will also happen to the batteries. Then you have to replace the batteries within a span of 2 to 3 years. If you're taken for the 5 years of guarantee, then you have to replace it by 2 years only if you don't monitor the temperature of the batteries, right? Next, efficiency and the range. Obviously, efficiency, if the temperature rises in the battery due to interrelation and the various factors, the efficiency will also decrease gradually. And the range of the nothing but the how much of range it is to give. Earlier it is to give the 100 kilometers or 100 miles. And now it is going to be reduced for the 70 to 80 kilometers per miles. Right? There is a proper cooling is very required to improve the your electric vehicle mileage. Right? If you don't make the cooling, no, and the fast charging, right? So it will leads to the reducing your efficiency and the range. Alright, so this is the reason where you have to see about the more on the batteries thermal management. Okay, so now we'll see about the how this will make a lot of impact on the key components of the BTML. Right? Why key What are the key components? Right. So what are the key components required for the BTML? So one is the temperature sensor. Correct. One is the temperature sensor where we are going to monitor the battery heat levels. Right. We have to monitor the battery heat levels at all the times. We have to see what is the battery conditions. We have to see the how much of temperature has been raised in the batteries. So, all right. So these are the various factors you have to see. What is the purpose of going to this BTMS? Right. So it will try to make the temperature sensor. Will try to sense the various parameters such as your temperature, and it will give the data to the measuring instrument. Then the data will be connected to the your BMS architect to the analysis purpose to the clouds. Right. So this sensor will help us to give a lot of information the how much of temperature has been raised using the temperature sensor. It will help us to find out the what is the value of temperature during the particular instant of point. All right. So temperature sensor, what it is actually, it will sense the monitor cells and cooling temperature. Right? Every 100 seconds, it will give the data. Right? So what is the purpose of needing this? Right? You have to see the what is the difference between the two cells. How much of temperature is there? If one cell is giving off a 45 degrees, and the other temperature is giving off around 10 degrees centigrade. Other cell is giving around 25 degrees. Then we have to see why it is giving that much of temperature. What is what is monitor? Why what is we are going to monitor? What is the action we are going to take? So that is the purpose. You have to see the temperature for each cell. That is 2 to 4 cells, or maybe you can randomly can check the cell's temperature also. Right? It will help us to study for us to understand how the BTMS can is performing for the checking the battery conditions also. All right. So when it's talk about the cooling of the cooling mechanism, right? So cooling mechanisms, we have the different types of cooling. There is the air cooling, we have the liquid cooling, we have the phase change materials, we have the heat factor. So these are the cooling components, right? So it will try to remove the heat. The purpose is to it will try to remove the heat by these methods. All right. So that is the heat nothing but what I square into R, isn't it? I square into R, right? So during the 50 kilowatt of if the charge for 40 fast charging is around the 20 kilowatt, what is the heat has been produced. So that is what you have to think, right? So this is all the techniques we have to think about if the temperature is raised. What are the cooling mechanisms we can implement? That is active cooling or passive cooling, right? Air cooling, liquid cooling, or PCM or heat pipes. Right? Then you have to implement the thermal insulation for the BTMS, right? So from the thermal insulation also we can safeguard your batteries. Ensure the proper even heating of distribution is happening in the batteries or not around the cells, and also to think about the battery pack design, how the battery has been designed, and also to think about the battery pack design to optimize the layout for the maximum heat dissipation. All right. So battery pack designs will tell us about the optimized layout for the maximum heat dissipation. Right now in this diagram, you can see there is a capacitors we have the heat sink, right? In the power electronics, usually we have the heat sink. Why we are going to use the heat sink? What is the purpose of using the heat sink? The heat sink will absorb the heat from the power electronic devices, and it will gives the heat back to the environment, right? It will send back the heat to the environment. So that's why even in the most of the electronic boards also we used to have the power semiconductors or power electronic devices where it used to deliver normal of heat. So that can be heat will be trapped by the heat sink, right? In this diagram, there is a heat sink, isn't it? So like that, it will try to trap the heat sink where it can absorb that heat and give to the external environment. Right? Like that also we have to have certain types of the cooling system, right? It may be of liquid cooling, it may be of air cooling, it may be of phase change material. So these are the different coolings you have to adapt for your thermal management system in the BMS. All right. So liquid cooling, where you can utilize the circulating of the coolant to dissipate the heat so efficiently from the battery cell to the during operation. All right. The air cooling, it also implies the air circulation to remove the excess of heat from the battery's components, which is suitable for the lower temperature periods, right? The phase change material also integrates the potential materials that absorb the heat during the melting, and also the maintaining the optimal battery operating temperature. All right. So these are the various. So these are the various types of the cooling systems where you have to see the different types of the cooling which is happening, different types of the cooling methods which can be incorporated over the BTMS. Alright, so let us see what are the types of the BTMS, right? By battery thermal management system types of the cooling can be happened. What is the one is active cooling, and there is a passive cooling, right? In the active cooling, we are having the external power, right? That will be hit directly to the heating area, right? It may be of air cooling or it may be of the liquid cooling, right? So liquid cooling, if we take the fluids where you can pass the when you do a manufacture of your cell, right? If you, for example, you take the cells, okay, cells which are connected in series and parallel combinations, where all the cells can be connected in series or parallel. So beside the cells, you should have a proper channel for the cooling effect, right? If you design in such a way, no, we can pass the any liquid or any like a fluid for the cooling the cells of each cells can be made a very cooling when the temperatures get rise. Okay, so that is called the external power external cooling can be happen, right? That is called active cooling. So in the passive cooling, it will absorb the heat naturally. Like for example, if it is semiconductor material, the PCM, right? PCM will try to absorb the heat and it will try to make the cooling in a very easier way and remove the heat from that material. All right. So again, we have the hybrid system, right? And the hybrid system also is a combination of these two, active cooling and the passive cooling. So where this cooling can be happen and it will try to improve the in a very faster way, it will improve the efficiency also. Right? If you take the hybrid system, no, one you pass the when you are going to pass the air to the heating element, right? What will happen? The cooling will happen. Right? Again, the temperature will be there, right? The temperature rise from the 40 to is the rise to 40, then it will come back to the 35 35 degree. All right. Again, if you want to come back to the 25 degrees centigrade, no, for the normal temperature, again you can apply the that is what was talking about the passive cooling, right? It will try to pass the PC materials. You can make the coolings in a very easier way, right? You apply the dual. If you apply the dual of the active and passive cooling, that will make the efficiency to be improved, right? That's why the hybrid system is also very useful for the cooling techniques, right? So these are the different types of the cooling techniques, all right? If you see in the active cooling, no, if you see in the active cooling, you may use the fans also. You can use, especially in the grid also. They are using most of the fans for the big transformers. For ABB also, they are using the big transformer for the cooling system. So, all right. So when you talk about the passive coolings here, we are thinking about the PC materials which works or a heat pipes to absorb the more heat, right? Isn't it? So there is no energy used from the this PC material. There is a zero power drawn, right? When you talk about when you think about the active cooling, no? So in the active cooling, especially there is a certain the power usage will be there around 1 to 3 kilowatt of power will be drawn from the fan to make the cooling for the your cells of the batteries. All right. So when you talk about the hybrid system, right? So it is nothing but the combination of the both active and the passive cooling. Right? So passive cooling is for the normal time plus the active will kicks the for fast charge or the hot days, right? Isn't it? So that's how there is a if you see about the energy usage, no, it is comes to be around 0.5 to 1.5 kilowatts for only when it is needed for the hybrid system. So let us see the different types of the active and the passive cooling, right? So we have the temperature cooling, we have the energy consumption cooling, and we have the heat dissipation cooling, right? And we have the these are the various methods where you can go for the active and the passive cooling. All right. So if you see in the temperature control, it will utilize the mechanical system like a fan or pumps to regulate the temperature, right? As I told for the temperature control, so it uses the mechanical, the big fans that is in the power grid also there is the big fans to cool the heating. So for example, you take the transformer, right? The transformer is loaded, heavily loaded. So what will happen? The current drawn from the load to the transformer, no? The transformer will be heavy loaded. So during that time, the power will be much power will be drawn from the transformer to the load, right? So the more amount of current will be drawn to the load. So that's why it gets heated up. So for that, we are building a fan to the transformers, right? So that's why the transformer is also called the mechanical system where it is makes the cooling for the transformer, for the transformers, right? For the windings. Similarly, you can use for the your vehicles also, right? We can put a fan, just like a motherboard. Also, we are putting a fan. Why? Because when the processor gets heated up, it will make the cooling for the entire your motherboards. So, where you can also use the fans for your motherboard also. Similarly, you can use the fan for your and the power grid also, right? So, similarly, you can use that fan for your battery cooling also, right? This is one of the type of the cooling system. It has as I told about the fan is which is making the active cooling for your for the active cooling, right, isn't it? So next we have the heat dissipation, right? So heat dissipation will make the natural convention methods of the radiations to dissipate the heat without any extra energy, right? Just try to dissipate the heat using some certain kind of the one is which is we can call it as a PC materials, right? So PC materials, what I told in the PC materials, does it takes any kind of the energy to make the dissipate heat. No, there is no zero power. It is taking the zero power drawn, right? The zero power, it is drawing the power zero. So that's why you can use the PCM for the making the heat dissipation, right? And also, when you talk about the energy consumption, right? It requires a more input to operate the cooling component, which maybe reduce the efficiency also, right? So that's why you have to think about the how much of power is drawn from the supply from the sources, right? We have to think about that one also for while making the cooling also, right? So when you talk about the energy efficiency, right? Energy efficiency will also matters a lot, right? For the energy cooling, thus maintaining the overall system efficiency. Now you can see in this diagram there is a different types of the fans has been fitted for the cooling purpose, right? When the temperature gets raised, it is trying to make the cooling the system, right? We have the cooling techniques, air cooling, liquid cooling, and the phase change materials. Right, I've been discussed all the already. I've been discussed the phase changing materials about how the phase changing materials can be functioned, right? All right, we have the air cooling, we have the liquid coolings, we have the patient materials, we have the active, we have the active control, we have the compact designs, we have efficiency monitoring, we have the cost analysis, we have the temperature distributions. All right. So these are the various techniques for the cooling your batteries also. Now let us see the air cooling, right? Isn't it? In the air cooling, we are using the ambient of air to flow to dissipate the heat through the convention methods. Right. So this is one of the methods where you can go for the air cooling ones, right? So air cooling will try to dissipate the heat from by the blowing the air through the convention methods. Okay. So next we have the liquid cooling, right? In the liquid coolings, there are the circulations. We have the coolant channels for the cooling effect, right? That is what I told in the especially BTMS. Most of uh, most of the BTMs they are using the cooling system where they are using the coolant for the cooling the all the individual cells, right? They are using the very coolant. They are going to use the liquid or any fluids to make the cooling for the each individual cells, right? So that will reduce your thermal behavior, right? And also we have the patient materials, right? And the patient materials it will try to absorb and release the enormous of heat during the phase transition, right? It will try to, there is no power consumption from these materials, right? It is just like a semiconductor material where it will try to absorb the heat and it makes the cooling and then it will dissipate the heat. So that's how the chain materials, the phase chain materials will try to work, isn't it? So next we have the active control, right? The active control will try to employ the different types of sensor dynamically to adjust the cooling system, right? It will try to respond based on the temperature. If the temperature is right, based on the temperature, the cooling of the system can be adapted. So it's just like it will depends upon the and it will study the environment conditions. It will try to monitor the temperature and it will try by using the sensor, right? It will understand what is the temperature now. Temperature is in rise or temperature is in decrease. So based on that, it will try to make the active cooling, right? It will try to respond based on the temperature. So we have the different types of it will try to make the efficiency monitoring also, right? It will cost and we talk about the cost analysis, right? So if we try to implement the more and more in the EV, the cost will also increase, right? So the cooling system is another part, right? Where you have to incorporate in the BMS for cooling the beat for thermal management system, right? The cost will also increase. So you cannot think about the more economic. So more cooling is required, the more life is required. Then you have to think about the cost also, right? So more it you cannot have the more economic loss, right? Isn't it? So when you talk about the temperature distribution, right? Ensure they should have the proper distribution across all the cells. But that is also very, very important. Always it will try to chances of failure would be there. All right. So this is actually the temperature response of the each battery cell, right? Cell A, cell B, and cell C has been given, right? So with respect to the temperature rise in the degree centigrade, right? That is how much of temperature is going to rise based on the each cell it is monitoring, and this graph has been taken from the battery cells, right? From cell A to cell D have been taken with respect to the temperature degree centigrade. Now we need to talk about the monitoring the temperature in the battery system, right? We can see there is a different types of monitoring system 25 degrees centigrade and we have monitored for the 40 degrees centigrade and we have been monitored for the 15 degree and 5 degrees centigrade. All right. So this is the various data we have been collected to make you to understand in a very from a clear way, right? All right. So here we have the maximum value we have from the month of maximum we have, isn't it? With the different month in the temperature. See, in the different month we have the different temperature reading for the bar chart. We can say the pie chart and the bar chart. It is giving a very clear data information for the monitoring the battery health condition of the batteries, isn't it? So if you see there is a monitoring around from 0 to 120 degrees centigrade the temperature. All right. So you can see there is a temperature is to be around 20 degree and then it is going to 40 degrees in the month of May. In the June also there is slightly changes. In the July also there is slightly changes and when it is getting decreased then also there is in the month of August. You can see the different temperature has been recorded at different time of the monitoring of the each battery cells, right? From the 25 degree to we have gone for the average of 25 degree maximum to 40 degrees centigrade. Right. So this is the data we have been collected to make it understand very clearly. All right. So next the active cooling. What is active cooling will make actually active cooling in the thermal management system will tell about the you are using a fan, right? As you are using a fan for the transformer as I told to circulate the air, right? And dissipate the heat very quickly. Especially in the transformer also they are fitting the fans on the especially in the generating station, right? In generating station they are using the fans because they are going to fit to the transformers, right? Where the more enormous of heat will be produced in the substation or it may be in the generating station in the transformer, right? So that's why they are fitting the fans to for making the cooling purpose, right? And it will try to dissipate the heat immediately. So this is one of the example where you can see the air cooling is also happening in the battery pack in the Nissan Leaf car, right? It is an electric vehicle, right? Where this cooling can be made very easier, right? If you use of the fans for the cooling technique, right? So active cooling are nothing but the liquid cooling, right? The liquid cooling where you can transfer the fluids across the each cells to try to absorb the transferred heat and can be distributed to the external environment, right? So the liquid coolant can be taken as a water glycol mixture, right? It will try to pass that liquid of the neighboring cells and also the besiding all the cells so that there is a chances of the cooling can be happen very quickly, right? These are the coolant you have to use for the to reduce the cell temperature. Whenever temperature gets rise now, you have to go for the cooling cooling purpose. Okay, so that is one. If we see if there is a parameter like there is heat transfer rate, right? The liquid cooling can be comes to be around 1,000 to 3,000 watt per meter square of K value. But air cooling is comes to be around 25 to 100 watt per meter square of K. Right. So what it really matters a lot. So liquid removes the liquid will remove the 30 times of the more heat handles for the 250 kilowatt of charge, right? So that's why we have to think about the what are the types of cooling can be happen, liquid cooling and also the air cooling, right? Isn't it? So that is what we have to think about the pros and cons of these types of the liquid cooling, right? So which is the more superior and which is the more complexity. So we see the pros, there is more superior heat distribution, right? Which is effective and increase the performance of the electric vehicles. So we see the cons now, there is more complex and costing expensive of the air cooling system, right? So example is in the Tesla models, they have employed the liquid cooling for the BTMS. But most of the cars, the Tesla, Nikola Tesla cars also, they have been employed the your liquid cooling BTMS system. Alright, next what is the passive cooling actually? What is the passive cooling is nothing but as I told there is no power is consumption from the these kinds of the cooling systems, right? Isn't it? So when you talk about the passive cooling, right, the PHN materials which can absorb and release the heat immediately. Right. PCM is stand for the phase change material, right? The paste in materials usually it is a paraffin wax or you can say the salt hydrides that will melt at the specific temperature like 35 degree to on or 42 degrees centigrade, right? So that's how the PCM will try to work, right? So it is fully based on the melting absorption of the huge heat. When it try to observe the heat, right, the latent heat of the for example 1 kg, the PCM will try to melt it will observe the 200 kilo joules also, right, without a temperature rise. So like ice melting at the 0 degree centigrade. When you keep your cold drink, right? Isn't it? Once only if you fully melt it, no, it will stop cooling and until the night when it gets solidified again, right? So this is how the passive cooling will occur, right? If you take the parameter, for example, if you take the parameter of the PCM, right? The parameter of energy use, right? That there is no power driven. That is zero watt of power is driven, right? So if you talk about the liquid active, right? It is around reduces the SOE of around 3 to 8% if you use this material. That is the state of energy can be reduced from the 0 3 to 8%, isn't it? So that is the one example I have just given to make you to understand to be very in a better way. All right. So other thing is that when you talk about the heat capacities, right, the PCM will try to make the limited for the 150 to 250 kilojoules per kg, right? That is a limited for mass for the heat capacity. Temperature control, when talking temperature control, it can stable up to, it can hold up to melt of temperature around 35 degrees centigrade also, right? And the response times it is more faster. The PCM is more faster. Sorry, it will be takes a minute to melt. It will not more faster. It will take a very slow times to melt the things to be melted. It takes more time to melt. Okay, lifespan if you say it will PCM will degrade after 3,000 to 5,000 cycles. If you think about the PCM, it will try to degrade its life. Once the life is of the cell is 3,000 to 5,000, no, it will start degrading. The PCM will start degrading with, after the usage of 3,000 to 5,000 of the cycles. Okay. If you talk the cost is very, very high, right? It is comes to be around 10,000 or 20,000 for each PCM, to weighing up around 8 to 12 kg, right? So that's how the PCM will try to observe and release the heat to the external, which is fitted in the electric vehicle under the BTMS and the architect of battery management system. All right. So one pros and cons if you see, there is no energy consumption, right? So there is no, you will not try to draw any energy, right? And it is more stable for the control also. So think about the cons, no? That is a limited cooling, right? Limited cooling can happen up to certain temperature, right? PCM will degrade over time when the life cycle get keep on decreases. Right. So it is used best example to use in the most of the hybrid electric vehicle. So you can use in the most of the hybrid electric vehicle. That is the far better to use it. Okay. So all right. Next is the passive cooling. Right. Next is the passive cooling and the hybrid cooling. We'll try to understand the thermal runway. Then you can go to the different types of case studies. All right. What is the innovation happening in the BTMS? Right. What are different types of passive cooling which is happening. So in the passive cooling, the same patient material will try to observe and release the heat. As I told, that is there is no chances of it is observed any energy consumption for the battery. That is not already been discussed. Next, we'll see the how the passive cooling will happen next with the heat pipeline. We will try to transfer the heat using the pipeline. The steel pipes will be fitted across the working fluids where you can pass your fluids inside the pipes, and also it will try to observe. It will carry out your all the heats to the inside the fluid also, right? So no extra energy required for this. It is very light and it is more reliable also. And if you talk about the cons, no, it is a limited cooling can happen in the batteries, right? It is a very less effective as compared with the active cooling, right? Under the heavy loads, right? Heat pipes are commonly used in the plug-in hybrid vehicles, right? In the hybrid cooling, if you see the hybrid cooling, these combinations of the both active and the passive cooling, right? For example, it is used in the most of the Tesla models, right? It is used in the BMW i3 also. These are the techniques where most of the EVs are using these types of hybrid cooling. Tesla as well as the BMW i3 also. Alright, next is the thermal runway, right? The thermal runway is nothing but the temperature which is rising in the batteries, right? It has to be, should be removed from the batteries, right? What are the causes and the prevention? Causes is nothing but the overcharging. Due to the overcharging also it may happen. Due to the short circuit also it may happen. Due to the mechanical damage in the cells also it may happen. That is, we are just talking about the electrode of the cells, right? And also due to the short circuit condition, due to the overcharging. These are various possibilities of the battery to get the degraded, and because of the thermal running, these are the causes for the battery to decrease its lifespan. All right. Okay, these are the causes and the prevention for the batteries. All right. So we have studied the active cooling. We have studied the types of under the air cooling, liquid cooling, and the passing of the PSM. We have studied the heat pipes also. Right? These are the examples I've been explained in the types of the cooling, right? The types of BTM, right? Active, we have the active coolings, we have the passive coolings, we have the hybrid system also, right? Now see different types of you have to go for the different types of the case studies. All right. What are different types of case studies you can undergo? You can find some research paper, okay? Study with the certain research papers and analyze the liquid coolings, which is the most effective for the performance of the electric vehicle. Try to get that from the research gap. You can try to find the problem statement from it, okay? A patient based on the cooling is also more promising, but requires the materials to be improved, right? Because it is a very, it doesn't require any power, and also it is doing the job of the try to cool the batteries in a very easier way. We can make the research also in this piece of materials. Okay, the student can do the research. You can do in the PBL also, right? So air cooling is also best for the low power application, right? Heat pipes offer a lightweight and alternative with a moderate efficiency. So these are the various case studies you can undergo for the student can undergo for the case studies, right? You can just take a screenshot of this so that you can understand your in a better way for to learning this. Okay, we'll see the comparison of the BTMS method. What are the comparisons you can make with the BTMS method? That the air cooling, liquid cooling, and the patient materials, liquid and hybrid cooling should be inserted in the column. Then you make the analysis with the by referring the various research papers. You can go for good journals, Standard, Elsewhere, and Springer, okay, IEEE. So there is try to refer and make try to compare of the different cooling methods, which is a better one, which what are different types of cooling has been used, and which is most suitable for the electric vehicles. Okay, you can make the comparisons of the BTMs for the different uh, cooling systems. All right. So what are the innovations which should be happen? Right? Even researchers have to make a lot of novelties in this. Still in the BTML, right? So AI is ruling the world, and also AI and smart coolings also make use of the real-time data collection for the controlling the temperature, right? The accuracy itself of the batteries, right? And also we use the nanometers for the PCM, right? And advanced PCM also has to be utilized. That is why I told about the lot of you can make the case studies in the PCM based cooling for the promising, but require the material improvement. We have to try to improve the materials to design the PCM. All right. So that is one of the things where you have to see how the materials can be designed to make the better one of the PCM that can be utilized for the electric vehicle for the cooling system. Solid. So that is what the nanomaterials and the advanced PCM has to be used for improving the heat distribution and storage. And also the wireless cooling techniques also can be used for the future enhancement of the battery cooling system, right? For the we can improve your potential of your battery cooling systems. But try to make the novelties in the wireless cooling technologies, and also the nanomaterials, and also the AI and the smart cooling system also, right? So that is the major things where you have to think about the cooling, how the cooling can be made in the novelties in the BTMS, right? So BTMS and electric buses. Most of the electric buses, if you see, where it is using high capacity of the batteries, that is to be around the more than 400 volts, right, for the electric vehicles. So you have to think about more heat will be dissipated, and also how the this can be overcome the BTMS for the advancement of the things will be required for the BTMS. Right? You have to think about the most of the problems which is occurring in the electric vehicle buses also in the trucks also, right? The heat generation, how the heat is generated in the electric vehicle for the 400 kilowatt of the battery, it is a 4 kV during the 50 kilowatt of charge, right? And also to see about the daily cycles also, how much of cycle has been reduced per day. You have to think about the downtime cost also. What is the cost um, for the vehicles which has been used for the downtime, right, isn't it? And also the pack weight also you have to think, and you have to think about the BTMS power which is drawn, right? Where it is drawing the power of 1.1 to 2.2 kilowatts, isn't it? So if we, these are the various factors you have to think for the e-buses, right? So if it is to be around a 25 kilowatt during the 250 kilowatt of charge, what is the cycles it is taking? 2 to 3 cycles, and what is the for the what is the weight of the, that is what the we have to think about the pack weight also, isn't it? How much of pack weight it can sustain for 5,400 kg for the five trucks for the sorry e-trucks of the vehicles, isn't it? So what is the BTM, how BTMs will impact on this? The PCM will fails to liquid if the weight if the for the especially for the 4 kilowatt during 50 kilowatt of the charge, right? The PCM fails to liquid mandatory. It is very mandatory that is the PCM will fail, right? So like that, if you think about the other also, right? When you talk about the other factors for the your BTMS, isn't it? So when you talk about the for but when you talk about the actual the daily cycle, right? So daily cycle if you use for the EV cycle, it may be around 2 to 3 cycles per day, and also for the tracks it may be around about 3 to 4 cycles per day. And how the BTMS will impact? It will impact on the SOH only. It will drop fast without seeing the that is the delta T. It may comes to around less than 3 degrees centigrade, right? So that is how you have to think about the BTS. BTS also means a lot of impact for the different types of the cooling, isn't it? So when you talk about the BTMS powertrain, right? So for EV car, if you take 400 kilowatt hour of EV car, isn't it? It is 1 to 2 kilowatt. So for the e-bus, it will be around of 8 to 12 kilowatt. For e-tech, it is around of 20 to 30 kilowatt. Right? So how the BTMS will impact? BTMS will impact on the most of the in terms of percentage. of the pack work for the uptimes, right? So that is what you're thinking about the types of the different types of the cooling for the hybrid vehicles, for the cooling commonly used in the commercial electric vehicles, right? For example, the Tesla which uses the liquid cooling package for the efficiency purpose, right? What are future trends, right? How the future trends can be adopted? Like try to bring the new cooling fluids and the materials which can improve the efficiency. Right? In the manufacturing field, most of the cooling materials which are used for the cooling the EV batteries, right, it may be coolant or it may be PCM materials. Try to make the innovations in the materials and also the cooling fluids to improve the efficiency of the batteries, right? And also go for the AI power, where the AI power will also make a lot of impact for the cooling system also, isn't it? So these are the various methods you have to adopt and also try to improve the cooling methods in the BTMS, right? So compact and lightweight design should be there so that anybody can purchase your the material to for the cooling purpose, isn't it? Now let's see what are the challenges in the implementing the BTMS. So what are the challenges we can go? What challenges we can make? That is the cost and the complexities, isn't it? The cost and the complexities of uh, the battery, right? Liquid cooling for liquid cooling and the hybrid system increase the manufacturing cost, right? And if you see the durability issues, some cooling methods degrades over the time, isn't it? And sometimes the extreme weather conditions also there is a cold climates and there is a battery efficiency also. So these are the challenges which will come to you have to think about the challenges how this will make a lot of impact on the cooling system. Right. So from this, what is the conclusion from our discussions? The BTM is essential for the EV performance, safety, and the longevity of the battery. And also, there is a hybrid cooling which offers the best balance of the efficiency and the cost. And the future innovation, they should focus more on the AI and on nanotechnology materials and the compact design. All right. When you talk about the future trends, right? The future trends, as I told, focus more on the battery enhancement system, right? Extend the life of the batteries and try to improve the battery reliability for the second life use. All right, and also the think about the road ahead also, all right, where the road is also plays important for the predictable future. All right, so these are the future which can be adopted for the in the upcoming days, right? Think about the more enhancement of the batteries, how the battery can be enhanced, right? So try to improve the battery enhancement systems, right? And try to we had to learn more about the how the SOC, SOH, and SOP, SOE, and SOF estimation can be done in the BTMS thermal controls, isn't it? And also think of the extended life for the batteries. So that is we have to think about the SOH tracking plus BTMS keeps the temperature at the active balancing for all the cells, right? And also think about the real life, the second life. That is accurate SOC and SOH and SOF will tell if the pack shapes are reals. That is what it will tell. All right. So next we'll talk about the road height, right? The road you have to use the GNN and the AI for the SOC, for the digital pin for the predictive BTMS. All right. So these are then if you see about when you talk about the how this the enhanced battery management system can happen for the where you have been learned for the SOC, SOH, SOP, SOE, and SOF for the estimation for the BTMS, right? So how to make the impact? It will try to take the real time GNN plus the sensor use the percentage of errors for the in the RMS value, right? Isn't it? When you talk about the our extended life, isn't it? Extended life, how it makes a future enhancement. So better batteries will test the if you, battery should be lost for the more than 8 to 12 years. You can give the life for 5 to 10 years. Nobody will buy your batteries, isn't it? So if you give the battery for the life of 10 years or 12 years or 13 years, everybody will try to buy your batteries of your company, isn't it? So that's why you can expect for the SOC for the 80% of the or end of the life for the 4 to 5 years, right? So that's why to improve the life of the batteries to be more improved, right? We have to promote for the circular economy for maximizing every battery operational life. So when you talk about the real second life, isn't it? Real second life, that is what 70% of the SOH will pack the certified for the solar storage, right? And no testing will be needed for the especially for the battery life. That is, we have to make the ensure the safe, efficient repurposing the EV batteries for the grid storage and the backup systems. So when you talk about the AI, that is the road ahead for the AI has to be forecasted for the self failure and the monthly early plan replacement should be done for the batteries. And then that is what the continuous AI innovation should be done for the right to greeneries to become a more predictable future for the e-mobilities. So, alright, if you have any doubts, you can ask me. Um, you can ask me from the any slides, right? So if you don't have any doubts, we'll wind up the class. If you have any doubt in any slides, you can ask. So I'll come from the beginning of the various slides. So where we have discussed with the different pattern of SOH and SOC also future predictions, right? AI ruling the AI in the world and how matters of SOH, right? And degradation of the batteries and how we have to become a masters in the state of health. What are different techniques have been used, isn't it? So these are the things we have discussed, and the two ways of estimation also we have been discussed. That is what the how the thermal management of electric vehicle can be done, and also what is it BTMS and what are the types of estimations we have SOC, SOH, SOP, SOE, and SOF. Right, and why battery thermal system is very critical. I already talked about the sensitive nature, runway risk, and also the performance and the life cycle, also efficiency and the range. And what are the types of management system? We have the liquid air cooling, we have the PCM material, right? Types of BTM, active cooling, passive cooling, and hybrid cooling also. In active and passive coolings, we have the temperature control, heat dissipation, the energy dissipation, and the energy efficiency also. Right, and these are the different types of the cooling techniques. That is the air cooling, liquid cooling, and the facial materials cooling. All right. You can see there is a fan also fitted for the, especially in the grid, they make use of this technology for the cooling the batteries in the HVDC stations. All right. So this is a response time for the battery, each battery cells. And this is the modeling temperature in the battery systems. We are taking for the 25 degrees for the average temperature and maximum to 40 degrees centigrade. For the different months, it has been calculated. Right, and these are types of the active cooling, and we have the in active cooling, we have the liquid cooling, passive cooling, we have the PCM-based material. The passive cooling, we have the heat pumps for BTMS. All right, and we have also have the passive cooling. We have the heat pumps, the BTMS. We have hybrid cooling, combining the different methods. Hybrid cooling, nothing but the no single method is perfect because of we go for the hybrid cooling for which makes the combination of the two techniques which can enhance the efficiency of the cooling system in the BTMS. All right. So example is the Tesla models, right? And then in the Tesla model we have the liquid cooling plus heat sink also. Heat sink, as I told you, wherever the heat is there, it will try to absorb heat and will release to the external environment very quickly. Right, in BMW i3 also, in BMW of electric car also, they are using the air cooling plus PCM based cooling, right? Air cooling is there, and also the PCM based cooling also they have been incorporated in the BMW car, right? So thermal runaway causes. What is the thermal runaway causes? As we told about the overcharging, there is a short circuit, and there is a mechanical damage also, and there leads to the we have to make the preventing this method by BMS with a high efficiency of BBT methods. All right, and this is let us see the case studies. We see the case studies. We have to find out the performance of the BTMS techniques. So that is the liquid cooling that is the most effective for the high performance of EVs. The PCM based cooling is a promising but requires a material improvement, right? And air cooling is also best for the low power applications. Heat pumps are often lightweight and alternative with a moderate efficiency. That is what you try to go for making a comparison of the different types of the air cooling, liquid cooling, PCM and all, right? And what are the innovations I told about the novelties? We have to try to make the novelties in the advanced PCM materials, which is a very complicated and we think about the nanotechnology for designing the nanomaterials, and then try to go for the wireless cooling technology also. All right. In the BTMS electric car, we had already discussed the capacities and the liquid cooling and types of the cooling system has been incorporated in the hybrid cooling also. They're used in the more commonly electric vehicles. Right, and these are future trends. Try to go for the future technology or the AI powered for adaptive cooling system, right? Where the data can be captured in the real-time data can be computed, and also the data can be driven from the each cells to analyze the pattern of the cells of the temperature, current, and voltages, right, and the life cycle of the battery, and go for the design of the compact and the lightweight of the BTR design. So that will help us to make very good things in the EV technologies, right? And so if we talk about the challenges, think about the cost, think about the durabilities and the weather conditions. Also, these are the challenges you have to undergo for the types of the cooling systems, all right? And there are different types of the cooling methods that can be degraded over the time. Durability issues also will occur. So think about the challenges to improve the BTMS and try to implement it, right? We talk about the conclusions, right? So future innovation is very important. Please focus on the artificial intelligence, the machine learning, and the nanotechnology. Go for the complex designs. And these are the future trends, right? I'll discuss about the future trends. That is a battery enhancement of the life of the batteries and extend the battery life, and also go for the reliability for the secondaries of the life in the EV battery. So if you don't have any doubts, I'll wind up the class. Okay, thank you. So these all these slides will be shared, and you can watch the videos also. If I missed any topics, okay, discuss about the most of the things in the SOH and SOC, and the most of the topic has been already covered. Already we have discussed today. We have discussed about the SOH, estimation techniques, and the battery safety mechanism also have been discussed. We discussed about the thermodynamic system, right? So these are the topics has been covered in the today's sessions. I hope it is clear to everyone. If you have any doubt, you can make the queries. Right. So these are the topics which is very useful for to do your people also. I can make the research also in this. And it's very interesting. Most of the research people, most of the research people are doing the research on the particular battery management system of the right. So by especially on the cells also battery pack where how to implement the various thermal management system also. The research is undergoing, right. So try to implement your research and make the innovations and the novelties in the this field of electric vehicles for the battery management system. So all right, if it is no, if you have any doubts, if you don't have any doubts, I just wind up the class. All right. So thank you for your patience to listening this session. All right. Thank you so much. Just you can disconnect the call. Thank you so much. I'm going to end the session. Thank you.